All right. So today I would like to implement a B-tree interface in C. So I don't know why I got wanted to do this. I know about B-trees. I guess I never really fully read up about them. So I kind of was like, oh, this is like a magic thing for me. So I thought if I learnt about it, it would be good. Um, I guess first things first, I should say I wrote up my notes and like everything comes from Spanning Tree YouTube channel. His video on bee trees. It looks like this. Very good video, like fantastic stuff. So if you want like proper understanding of what's going on, good video to watch this one. But anyway, so I'll just go through like major ideas and then we can like get specific when we actually get to coding it. So I think easiest way, I think using BSTs as a way of motivating this or like introducing B trees is probably a good idea because I feel like most people who are looking at B trees probably will know what a BST is, probably a binary search tree. Just to give some background, a binary search tree, is a data structure, a tree data structure, so like a specific, like a special type of graph, basically with nodes and edges or vertices. Um, each node has a key which defines it. So today I'll probably just be using integers the whole time, but keys can be anything technically. But has some kind of key. Edges connect the nodes together, of course, and because it's a tree, this kind of tree-like structure, each node has exactly one parent node, except for the root node. So if we look at like these kind of trees over here, you can look at any particular node besides the very top one, besides the root one. Any particular node will have one parent kind of above it. So the 15 has the 10, the 5 has the 10, the 3 has the 5. We will never have a case where like you've got two parents that point to the same kid. Like that won't happen. So every node besides the top node, besides the root node, has one parent, exactly one parent, and then each node has at most two children. This is why we call it a binary tree, because every node, you look at any node, and this is true for any of the nodes, has at most two children. So the 10 has two kids, 5 has one kid, the 4 has zero kids, but you have at most two children, any particular node. And then the reason why we call it a search tree is because all the nodes in the left subtree of a particular node have a smaller key, right? So if I look at the 10, if this is the node I'm focusing on, if I look at the left subtree, that is the left kid and everything that descends from the left kid, all these numbers are smaller than 10, right? Anything in the blue, right? If I look at the 15 over here and I focus on the left subtree, that is the left kid and everything that descends from the left kid, everything is smaller than 15 in the blue. And then similarly, on the nodes in the right subtree of a particular node, those nodes will all have a bigger key. So again, looking at the 10, everything in the right subtree in pink is bigger than the 10. And then similarly, same kind of thing over here. If I focus on the 15, everything in the right subtree, which is just the 17, is bigger than the 15. So we call this a search tree because like with this very strict, or maybe I should say like, if I look at the 15, for example, if instead of a 13, I wrote like an 8, right? This might seem okay because the 8 is smaller than the 15. But you got to think about things like, you got to zoom out a little bit and say, well, yeah, that's cool, that 8 is smaller than the 15, but everything in here should be bigger than the 10 as well, right? So we're very strict. This 8 is smaller than the 10, so it's not allowed to be in the right subtree. Even if it is, smaller than the 15, it's meant to be bigger than the 10. So, this is a very strict sort of organizational thing. So essentially, what was I saying? Oh yeah, this very strict organization of numbers basically means if we ever want to look for a particular number in the tree, let's say 4, we know that like at any particular point when we're at a particular node, we know strictly in what direction we have to go. So if we start at the root, we always will start at the root, right? If we start at the root node, we ask, okay, this number 4, I'm looking for the number 4. Is it smaller than 10 or bigger than 10? Smaller, right? So we go to the left. And then same thing, we ask the same question. Is 4 smaller than 5 or bigger than 5? Smaller, so we go to the left. And then is it smaller than 3 or bigger than 3? It's bigger than 3. So we go to the right and it's like, oh, we found it. Like that's the kind of idea. And if there's a number that doesn't exist in the tree, like let's say we look for 2, we would say, is it smaller or bigger, smaller? Is it smaller or bigger, smaller? Is it smaller or bigger, smaller? And there's nothing here, which tells us that at that point, it tells us the number 2 doesn't exist in the tree. So, this idea of like organizing the numbers very strategically lets us find those numbers quite quickly, is the idea. Because you don't have to look through every single node. You only have to, you almost halve the number of nodes you have every time you go down the tree, is the idea. That's the goal, at least. And just as a bit of terminology, if you're a node with no kids, you're called a leaf node. Just following the terminology of trees, I guess. The nodes with no kids are leaves. Okay, so that's like background. And then B trees basically take the idea of a BST and try to almost generalize it. Like it's a more general form of a BST almost. So there's a hyperparameter n that is defined. And basically, so hyperparameter just meaning like you as the creator or you as the user will set the number of n. So a node can contain at most n keys. So here, every node had exactly one key in it, right? 10, 5, 15. In a B tree, a node can contain more than one key. It will have at most n keys. And all non-root nodes must have at least the floor of n over 2 minus 1. Where this number comes from exactly is like, it will make more sense later, I think. But for now, just understand that there is a minimum number of nodes all the non-root, the non-top nodes need to have. There's a minimum, did I say nodes? There's a minimum number of keys, sorry, that all the non-root nodes need to have. So you can imagine for all the non-root nodes, they have to have somewhere between this number and n number of keys. A node will have at most n plus 1 children. So here we said, you have at most 2 children. Here you'll have at most n plus 1. And this is kind of by necessity. This isn't like by design. This is like a necessary trait that we'll see. And then all leaf nodes, that is the ones with no children, are on the same level of the tree. So this last constraint is about balancing. So, I said generally when you sort of traverse down the tree, you basically remove half of the tree each time. That's not strictly true because, for example, a valid BST is something like this. 1, 2, 3, 4, 5, right? This is valid in terms of like, if you look at all the properties, I haven't violated any of them. For every particular node, if I look, the left subtree is technically empty, but anything to the left is smaller because there's nothing in the left, and everything to the right is bigger, right? This subtree, everything is bigger than the 1. In this subtree, everything is bigger than the 2. In this subtree, etc. So this is a valid BST, but it is basically a linked list at this point. Like, it's just a list. So if I had to look for the number 5, I'd have to basically iterate through every node, which is annoying, right? You don't have to do that. The advantage of BSTs traditionally is the fact that we have this branching structure where half of the nodes are on the right side, half of the nodes are on the left side. So if you end up getting a BST that looks like this, you're not really taking advantage of the BST. So we have this idea of balancing to try and avoid this. Balancing, sort of, without being too precise with my language, balancing is this idea of trying to maintain this level of symmetry. Instead of having a root node and then just everything on one side, you try to have this kind of balancing effect. So this tree over here is relatively balanced. Maybe there's some stuff you could do to make it a bit more balanced, but generally this is not too bad. So the idea of trying to have all the leaf nodes on the same level is basically trying to achieve this, rather than having, one sort of path to a child being like a leaf, being down here, and then the other one being really, really long down here. Then, in the worst case, if you have to look for a particular key, you have to go down this particular length. You would rather something like this, where in the worst case, everything's kind of on the same level. So your worst case is kind of minimized. So that's kind of the idea with that last condition. You're trying to introduce some balancing. That's the only thing in B trees that isn't specific to BSTs, I would say. That isn't like a generalization, because BSTs don't necessarily enforce balancing. Okay, so as an example, this is a valid BST. Notice how, so n is I've set n to 4, right? I've made that decision to set n to 4. And the idea is the top node, you can see that root node has 4 keys in it. So that's valid, 11, 43, 65, 89. And the idea is that means this node can have at most 5 kids, right? And the reason why there's 5 children, well, you can have 5 children, is because if you have 4 keys, there's basically 5 points of comparison, right? Any particular number that isn't in this root node can either be less than 11, between 11 and 43, between 43 and 65, between 65 and 89, or bigger than 89. So in that sense, like if you're less than 11, you should go down into this yellow path and be like somewhere in this subtree. I've only made one more layer, but you can imagine that this could branch further and stuff. But the idea is anything less than 11 should be in this subtree. If you're between 11 and 43, you should go in the green path. If you're between 43 and 65, you should be in the blue path, and etc. Right? So that's why there's 5 points of comparison, and that's why you can have 5 kids. If you've got 4 keys in here, then you should have 5 kids. And similarly, if you have 3 kids in here, if you have 3 keys in here, you'll have 4 kids, because 1, 2, 3, 4. But if a new key gets added to this, which is allowed because you're allowed to have 4 keys, then you'll have an extra kid that you need to draw up. So that's where that comes from. And then, this is just saying, note how the numbers are organized, this idea of these points, I've like specifically drawn them so that they're between each number, the edges, that is. They're points of comparison. So that's how the numbers are organized, which is kind of similar to the BSTs, right? If you go to the left, you're going smaller. If you go to the right, you're going bigger in that sense. If you're going in this particular, whatever particular edge you're going in, tells you kind of what range of numbers you're potentially sort of going between. Okay, so I'll probably start there. We'll talk about, and then the 2 major operations are insertion and deletion, being able to add numbers to the tree and being able to take away numbers from the tree. But I think we'll start with just trying to build this general structure. So my thinking, I've thought about this a little bit, is basically, of course, we have the overarching struct. So like we have the B tree struct. And then from there, I was thinking, we have our nodes. And the way I thought about this was a node will have maybe like an array of keys, right? Because with size at most n, right? We'll give enough space to fit n keys in this array. And for now, I'll just hash define the key, the n value, sorry. I won't make it like a proper hyperparameter. I'll set it as a constant. But eventually I'll use my command line arguments to take the n value as user input. But anyway, so yeah, we'll have the BST struct. We'll have the B tree struct, and then the nodes, which contain an array of keys. And for a key, of course, a key might just be a number. But I'm thinking what I could do is I could have sort of we'll say integer for now, int for the actual value of the key. But then also, so this is another struct, but also I was thinking we could have like a pointer to another node. The reason for this is I'm thinking, okay, let's say we're looking at 11, 43, 65, 89. These are my keys, right? Inside a particular node. The 11 specifically could point to this next node over here, 257. The 43 could point to the green. The 65 could be what points to the blue, and the 89 could be what points to the pink. And then the idea is, if I'm traversing down a particular edge that a key holds, then that means that I'm going to a subnode, I'm going to a node where the numbers are less than, the 11, and then less than the 43, and less than the 65. I believe this design will let me traverse the tree as I want. Of course, when I said all that, I ignored the orange. Right, because the orange is bigger than everything. An edge that is connected from a particular key, I'm saying, is pointing to a node that is less than the particular key, right? So like the 257 is less than the 11, 17, 29, 31 is less than the 43. So that last node here, which is bigger than everything, won't be associated with a particular key, but rather will be associated with the node. So like this will have a pointer to the bigger than child node. You know what I mean? So like this guy will be a field in the actual overall node as opposed to a particular individual key. I think this will work. Another option would be to like have an array of pointers in the node struct, so like have an array of edges basically in the node struct. But I think this might be a little bit more elegant. I'm not really sure. I'm just guessing, but I think this could be a good idea. Anyway, so it points to another node, pointed to specifically a child node holding keys less than this key. Okay, so that's what that idea. So I think that's a good start. Have the ability to create an overall B tree struct, then have nodes and keys, where a key, of course, has its particular value, but also the ability to point to a child node. And that should be a way for me to structure and traverse this tree. So let's get started. So I need 3 structs. What did I say? I said I want... This will probably just have a root, so I need everything else. Struct btree node, and then struct btree key. And like I said, I'll hash define, what should I call it? Max keys. This is like my n value. And we'll say you can have at most 5, or maybe 4, because I said 4 in my example, didn't I? And what did I say? So I'll type def everything as well. Okay, so btree key becomes btree key, and then btree node becomes btree node, and then btree becomes btree. Okay, fantastic. So a btree key will have a btree node pointer pointing to the node that is holding keys that are lesser than this key. So btree node child, I guess. And then of course you also have your key value. This will eventually become like a void star thing so that you can generalize, but for now we'll keep it as, unless I want to, maybe I was going to say like type def btree key type or something. And then we can be like int I don't know. It should be fun. Okay, so we have that. And then what did I say for a node? An array of keys, right? So btree key, it's going to be an array of pointers that point to keys. What I want this to be a linked list, actually, now I think about it. Because I'm going to have to be able to insert, I'm just thinking, because ahead, like in terms of insertions and stuff, I don't want an array, do I? Because I'm going to have to, when I delete stuff, yeah, it's going to be a linked list. Okay. New plan. It's not going to be an array of keys. It's going to be a linked list of keys. Because we'll see with insertions and deletions, we need to be able to delete things very quickly, oops, and insert things very quickly. So an array probably wouldn't make a lot of sense. So I need a linked list thing. So I should probably have btree key next. Is that fair? Because then I can link these up together to make my list. Whoops. I can link these up together to make my list for a particular, to build up a particular node. The node will point to the head, like that, so that I have my linked list structure. And then this guy also points to a child, which is talking about the node, the child node. That's fine. Am I missing something? Btree node. It will also point to another btree node, the greater than child. So if you know you're trying to traverse the tree and you have to go you're looking for a number that's bigger than all of these numbers, you have to go to the orange edge. Is the idea. So that's what this will point to. And then this will be B tree node root. I want like a size thing as well, maybe. I don't know. This struct looks a bit boring right now. That's all right. I also want to keep track of the size of so the number of keys, because that's going to become important. So num keys, which I will put down here because of alignment reasons. And I will do the same over here. Okay. I don't know if this is fair. Maybe I do want a size. Surely it can't be that hard to keep track of the size of things. Size basically meaning the number of nodes specifically, and this will have the number of keys per node. Or do I want the number of keys? Num nodes. Num keys? Is that annoying to keep track? But it might just be nice for like short circuiting reasons and maybe debugging reasons as well. So I'll just keep that. Just keep those fields. Okay, so that's my structure. Now, let me try making an init function. So btree pointer btree init given nothing. So all I'm going to do for the initialization function is create the btree structure. Num nodes is 0, num keys is 0. The root, should I just make it null? Is there any point in making it an empty, completely empty thing? Probably not, right? Okay, we'll make it null. So malloc size of the btree. Nope. Btree tree. I need a pointer. Tree equals that. And then tree num keys equals 0, tree num nodes equals 0, tree root, the root node of this tree is null. Yeah, should be good, right? And then return the tree. The tray. Good. Okay, so we have an ability to initialize stuff, and maybe I can free stuff as well. btree free given, wait, no, this is void, sorry. Given a btree tree. Okay, so what am I planning on mallocing? Eventually I have to free the actual tree for sure. But then before that, I'm probably going to have to malloc. Freeing is actually kind of annoying because I have to traverse everything. I have to do like a bottom-up thing. So it'll be like, for each key, travel down its thing, free it. Yeah, I'll probably do this recursively. So if yeah, I'm gonna need some given a btree node. This might actually be a bit more annoying than I first thought. So what am I saying? So the root is equal to tree root. So we have the root node, correct? Yes, we have the root node. And the idea is should I call this, whoops, and be like, what? btree node free. And the idea is in here, before we actually free this node, we first go through the linked list of keys and use those keys to travel to the children. B tree key current is equal to node head. While current is not null, current child, which is a node, if I say B tree node free and call the child, I think this will work. We free the child, we free the subtree, free everyone down here. Then we free this key. A bit nervous that I'm gonna accidentally double free stuff. So we travel down, we free this. So we get the key, we travel down the kids, we free all that. Then we come back. I think it's fair game to just be like current next, and then free so previous equals current equals current next, and then free the previous. Just like using previous as a temporary. So that should help us free up the linked list as well as the kid. And then also node greater than child, we're going to B tree node free the greater than child, which wasn't associated with any particular key, but rather is the greater than. It's that orange guy again. We've got to free that. And only then can we free this node. I think that's fair game. So that makes sure we free, so we were able to free the key, right? Because previous was that current. We're freeing the keys, we're freeing the nodes, and then eventually we're freeing the outermost structure as well. So hopefully that's good. So this is like the public thing, and then this is like the helper recursive thing. Okay, so that's pretty much the major ideas. So right now, what we're able to do is, what are we able to do? We're able to create a B tree and eventually we should be able to free it. Fantastic, right? Okay, so we've done that so far. Now, bearing in mind, I have to remember that the root node can be null. That's how I've set it up. The root node can be null, especially at the very, very start, so I've got to be careful. Okay, let's make the insertion now. So we should talk about it a little bit. So of course, the insertion operation, the idea is you're trying to add a key, specifically a number to the tree. So given a new key, which I've labeled K, right? You want to traverse down the tree until you find a leaf node. Whoa, okay. Until you find a leaf node. So for example, let's say we wanted to insert 63. This might be the same example as from the video. So I might be slightly plagiarizing, but I need to do this for me as well. So traverse down the tree. So, 63, for example, we're saying, okay, is 63 straight up less than 11? No. Is 63 less than 43, but bigger than 11? No. Is 63 between 43 and 65? Yes. Which tells us we have to go down the blue edge in order to put the 63 in the leaf node. And if this wasn't a leaf node, we'd repeat the process until we found a leaf node, right? We would iterate through the keys until we found the leaf node. Okay. We place K in that leaf node in sorted order. So this is why a linked list is better, because insertions are way easier if it's a linked list. I just iterate and then insert rather than having to iterate, insert, and then like shift everything down if it's an array, right? So put things in sorted order. So normally that would be the end of it, right? In this case, with a maximum of 4, if I was to insert 63 sort of at the end over here, that'd be no problem. However, we have to care about what happens if the leaf node overflows. Remember, we have that hyperparameter telling us how many keys you're allowed to hold before you start to spill, right? Like the maximum number of keys you're allowed to hold. So if the leaf node overflows due to the insertion, like in this case, this is different, but imagine you have a node like this as a root node who has all these kids, 1, 2, 3, 4, 5, and then this is the leaf node we care about, right? Inserting the 65. And by inserting the 65, it overflows, right? There's 5 keys in here. So if there's an overflow, we have to split this leaf into 2. right? The left leaf after the split gets the left half of keys. These guys. These guys. Left half of keys. The right leaf after the split gets the right half of keys. These, oops, these guys, right half of keys. And the middle key gets pushed up to the direct parent. The 60 in the middle will get pushed up and be inserted to the parent. So this is what it'll look like. The 40 and 50 got, so this leaf got split, the 40 and 50 came here, the 65 and 70 came here. Notice this green edge? That green edge wasn't there before, right? The yellow, pink, blue, green, and orange all were there. But this extra edge has to be created to be in the appropriate place. The 60 from here got pushed up and inserted into this node. Now, I've specifically drew out this example because notice how it's the parent now overflows, right? The child is now good because we split it appropriately, but the parent now has 5 keys in it, which is also a problem. So if the parent overflows, as a result, we recursively apply the same process. We understand that we can basically think of it as we inserted a 60 into this node, the same we inserted a 65 into this one. So we inserted a 60 into here, so we do the same process. We split the node, right side, left side, and the median or the middle one goes up. So we kind of get something like this. The 60 and the 71 get split, make one half, 73 and 74 make the other half. The edges, I've tried to sort of map them out so that they kind of match up with what's there before. And then the 72 gets pushed up and we actually create a new root node in this case. And the red edges are new as well. They weren't there before. They're a result of the new root node being created. So a note from the video that I thought was important to keep in mind: the only time the tree is meant to get taller is when this overflow happens in the root node. So in this case, there was some overflow in the bottom, but then it was the overflow in the root node that caused that extra layer to be formed, right? So that's something to bear in mind because of reasons. And then bit of extra checking if there's an odd number of n. If n is an odd number, the hyperparameter, so overflow happens when there's an even number of numbers, even number of keys. So for example, imagine you have let's say n equals to 5. So then overflow happens when you have 6 numbers. So let's say 1, 2, 3, 4, 5, and then you try to insert the 6, and that's what causes the overflow. Because there's no perfect middle number. Like here, there was a perfect middle number, right? You could take the 72, and before that, you could take the 60. What you do here is you just put a bit of bias. So, I think you can pick either one, but I would probably pick the 3 as the middle number, and then the left split gets 1 and 2, and the right split gets 4, 5, 6, and the 3 is the one that gets pushed up, right? So that's the general idea. So that's all the notes I had. I think there's stuff I'm going to be missing, and we'll see what happens. But right now, what we will do is we will try to implement this. So, I think this can be. This has to return. Actually, now that I think about it, this will need to, because you can potentially create a new root node when you insert. I think this has to return a B tree star, or at least maybe not actually, because the B tree acts as like a wrapper, so everything can happen within the B tree. I think. To void, B tree insert given a key and of course the B tree. Okay, so step 1, find the leaf node. Step 2, insert the leaf node. Step 3, split as necessary. If the direct parent overflows, split that as well, and keep doing that until we're fine. So there's going to have to be some level of recursion. Probably could use a stack if you wanted, but I will do this recursively because I hope it will be easier. Not as much data structure to keep track of. To find the leaf node. So this is going to be our first sort of real test of traversal. So we'll get the root, so tree root. So what am I doing? B tree node root is equal to that one. So I have the root. And then I guess I have to recursively... No, I don't have to do this. I can do this iteratively for sure. Surely. Maybe I'll call it current as opposed to root. And I'll say current. Okay, so... if I feel like I need a function that tells me if something's a leaf or not. Because I feel like it's not necessarily obvious. Like, if you have n plus 1 children, then for sure, like, you can just look at any key and it should be attached to an edge. It should be attached to another node. But potentially, some keys won't have any edges. Oops. And some keys will, you know, because it's not necessary that you have every key be an edge. So maybe actually what I can do is I can say for a node I can have a Boolean key that says has kids or is a leaf. That way I can just sort of, if I can keep track of that field very well, then I can just look up that key. Yeah, so if cur is leaf is false, then I have to be like, iterate through the keys, which means actually I should probably, but root can be null, I have to remember that. Okay. If tree root is null, then what? Then I have to be like malloc size of tree node yeah, so tree root equals to that guy, and then tree root head is equal to malloc size of b tree key, and this guy's next is equal to null because that's the first guy. This guy's child is also equal to null, there's no children. Key is equal to the given key. Okay. So this is creating the key. This is creating the root. The number of keys is going to be equal to 1. Is leaf is going to be true because if the root node will have no children at this point if there's only one key. Greater than child is also equal to null because there's no other nodes to point to yet. Number of keys is equal to 1. Is leaf is equal to, yeah, so I've done all this, right? And then I did the head thing last. And then there's a couple more fields. Number of nodes is equal to 1, and then number of keys is also equal to 1. This is the very first key we have added to the entire tree. So doing this should mean that I have inserted my very first key. And this is like always going to be the case, I think. Okay. So before we even continue, let's try that. So B tree insert, given the B tree, and given a key, like 7. So if I go like, as a helper, if I go like void print a node, which is basically just printing the linked list of keys given a particular node, we can be like B tree node current equals to the node, and then while current print f %d arrow rather while current next. Sorry, hang on. I need to get the head. So key node head. If not current, then return because there's nothing there. Otherwise, while current next, print up this comma current key value, and then you keep doing that, and then you get to the very last one. This guy will be non-null, and this will terminate when current is the last node, and then we'll just printf %d \n current key value. So that'll actually print out a particular node, which is cool. So if I do insert this one, and then I say print node given the B tree's root node, let's see what happens. So clang, and then it's not much, right? Oh, I did say 7, right? Okay, the good news is that seems to have worked. Bad news is I broke something. Okay, I was a little bit, I don't know if this will work now. F sanitize. No. Okay, still have to fix that. I forgot about that actually. Okay, we can add a debug. We can do some debugging straight off the bat. I shouldn't have this though, should I? Oops. I would assume, if I had to guess, I would assume it's from the freeing, just because I feel like that's the part I was most uncertain about. Yeah, okay. Unless it's the init. Maybe I messed up the init. That could happen. Okay, so it's probably the freeing. Breakpoint. I need to make a little launching thing. Sure. Oh, it did it for me. Interesting. I didn't expect that. Anyway, I thought I'd have to set up like the... Anyway, it doesn't matter. So we have the tree. The root is null. Interesting. So I'm assuming what happened is... So I'm trying to free this node, but the current should be null. Oh, okay. Right. I didn't have a check saying... Okay, that's fair enough. So if... the node itself is null, then I think we can just return. Otherwise, get the head of the node while it's non-empty, while this linked list is non-empty. Yeah, I think I prefer that. I mean, I could make it so that the root is always non-null but has no keys in it, but I just feel like that's a bit... I don't know, maybe that's better. I'll leave it for now. There you go. Okay, so if I do that now with this, do I still segfold or what? Okay, should be fine. Okay, so I think that was just some... I'm surprised though, because this time I would have had a root though, no? Like when I had these lines, I wouldn't have thought this would... segfaulted still. Maybe because, no, because when it traversed, it would have gone to the child, but the child would have been null. That's what it is. Okay, I understand. Yeah, fair enough. Okay, so that's not bad. Okay, so we're able to insert into the root node, assuming the root node is null. Okay. Otherwise, like this, if the current is leaf is not true. So if it's not a leaf node, if it has children, then I actually forgot my entire structure. So what am I? This is a node. I have to go through the keys. And I'm assuming that this has at least one key in it. Otherwise, this would be very strange. Okay. So B tree key or head is equal to the current head. Yes. While current key should I say while it's not a leaf? While it's not a leaf, B tree current key equals current head, while current key iterates. So if current key if the value is bigger than, if it's equal to the key, then just return, I think, because that means it's already there. Otherwise, if the current key is greater than this key I'm looking to insert, then that means we have to go to this child. Because remember, a key will point to the node where the numbers are less than that key. Right, so 40 and 50 is being pointed to by the 60, 71 is pointing to the 6570, like that. So if the incoming key is smaller than this current key, then current key child, what am I saying? Current equals this current key child. And break out. Otherwise, we can say current key equals current key next. And if we get out of here and we never if current key is equal to null, then current node, I should call this current node because I feel like I'm going to get confused. Current node is equal to the current node's greater than. Because the idea is, the key we're trying to insert is belongs to the orange edge. Now I have a slight concern because I just realized something. If I'm I think I forgot something. Hang on. Does it have to be a leaf node? I feel like I've misremembered something. Let me look at the Geeks for Geeks. Where's the thing? Okay, so in this we'll discuss the insertion operation. A new key is always inserted into a leaf node. Okay. But what if... Okay, so my concern, I should probably elaborate on myself. So basically, imagine I have a tree that looks like this. And then you have something like this. Right, so you have like a key over here, a key over here. Yeah, let's say there's two keys, so there's three edges, right? My concern is how does it work? Every time you push a key into the above parent, like because of the splitting and the pushing up to the top, every time you do that, that parent is going to point to the left split. Does that make sense? So like in the example, when we did this whole thing, the 60, when it got pushed up over here, it was going to point to the 40-50, right? Because the 40-50 is smaller than the 60, so the 60 should point to that. The 71 will still point to the right split. The edge that you traverse down to get to the leaf node, that edge will point to the right split of the node, 65 and 70, the right split. So that edge is still there, it just points to this. So we should recycle this entire node to just hold the 65-70, and we should make a brand new node to hold the 40 and 50, and the 60 should get pushed up to the top, pointing to the 40-50 node, I think. And then the idea is, when this happens again, when we have to recursively apply it to the parent, do the split on the parent, the 72 will point to this 60-71 split. And the parent node, yeah, should point to the 73-74 split. Either we'd have to create a brand new route, potentially, to point there, or there will be some other parent already up there that will already be pointing to this node. So I think, so long as I ensure that, so after a split, the parent points to the right sort of half, and the pushed up key points to the left half, I think, is the idea. Okay, so let me look at this. So while the current node is not a leaf, B tree current key is equal to current node head. So we go to the head of the head of this current node, the head of the linked list. We iterate through the linked list. If we find the key, then there's no point doing any insertions. If the current key is greater than the key we're trying to insert, then we should go down to the child and break out and restart. Break out of this while loop and restart this entire thing, yep. Otherwise, move on to the next key in the linked list. And then if we get all the way to the end, then that means we have to traverse down the bigger than. Hopefully that's correct. I feel like there's a bit of voodoo magic going on, but I think this is right. Anyway, when we get out of here, hopefully we'll have a current node that is a leaf, is my prayer. Like, hopefully we haven't just like gone somewhere random. So yeah, hopefully current node is a leaf. And the idea is, like, we got to eventually hit a leaf, right? Like, surely. We need to insert, so I'll make a helper. Insert into node, or B tree node insert. So given a B tree node, and given a key, we have to be like, I just realized, is it possible? Oh, I have num keys already. Okay, good. So B tree node I have to do the same sort of iteration again, right? So B tree key, sorry, current key is equal to node head. If the so while the current key's key, or maybe while the current key is non-null, if the current key's key is greater than the actual key, that means this actual key has to be inserted before this current key. That means I need a previous, don't I? So the previous key next should equal to the new key, which I have to malloc. And the new key next should equal to the current key. That is, if the current key's value is bigger than this incoming key. Because it's already sorted, so I just have to find that spot where we get too big and then we insert it. We insert the new key in between. So B tree key star new key is equal to malloc size of key B tree key. Is that fine? New key. So the key value is equal to key, and the new key's next value is null, but we'll set that eventually. Child is null for sure, right? Because we're in a leaf node. We should be in a leaf node at this point. So we're not going to be pointing to anything. New key next is going to be set to something for sure. So we'll leave that for now. Maybe I won't. So we created the new key. If the current key's key is bigger than this incoming key, then if there's a previous key, you have to link the previous keys next to the new key, and then link the new keys next to the current key. That way you're kind of putting the new key in between the previous and the current. If there is no previous, that means that you're at the head. So all you're doing is I gotta be careful actually now I think about it, because if there's a previous key, then do this. So new key next is always going to be the current key, if this is true. Else, if there is no previous key, that means you're at the head. This new key is going to become the head of the list. So I think I have to say node head is equal to the new key. I think I have to say that, because otherwise I think bad things will happen to me. Like, the head has changed. If I'm inserting this, if this is the smallest key in the list, I'm going to put it at the very start. The head has changed, so this has to do that. This will happen in both cases. Previous key, bang, bang, and then can I break out? And if this doesn't happen, then we'll move the previous key along and we'll move the current key along as well. And eventually, if current key gets all the way to null, that means we haven't inserted the thing yet. We got to the end of the list and something bad happened, which means previous key next should equal the new key. And the new key next should equal null. Just add a comment in here saying got to the end of the linked list without inserting. Okay, so we have this idea. I feel like I missed something. I feel like something was annoying me now, and then I forgot about it. Wasn't there something else I had to do? We inserted the guy. If we go to the end of the list, we have to put this at the end. Oh yeah, the node fields. Number of keys should increase by 1. Greater than child. Well, that's always going to be null because this is a leaf. Is leaf should be set to true, I think. I'll just say pretty sure this should. Oh, that's not actually true, actually. Because like, I'm a bit nervous actually. I don't think I can say that because I'm going to be inserting stuff into their parents as well when I do the splitting, and I want to be able to use this function regardless. I think that just can't be this function's responsibility. I'll increment, but then keeping track of all the pointers and stuff is someone else's job. Okay, so what are we up to? So if the tree root is null, then create the thing. Cool, create the root and create the key. So this is creating the node, this is creating the key, right? And then otherwise, find the leaf node, hopefully. If the current key is equal to null, then the current node is equal to current node. Yeah, so eventually we get out of here and we found the child, the leaf node that is, and then we give that current node and the key, which is an integer, and we insert the malloc thing into the linked list. Now what? If current node at this point exceeds the max keys, sorry, I said that wrong. If the current node's num keys exceeds the max keys, then we have to do the splitting. So we've done this. Now we have to do this part, split as necessary. So I want to be very careful about this. I probably want the parent node, don't I? I need the parent to be able to push up to the parent. So then, but I didn't keep track of the parent at all. Maybe I can keep it. Maybe I can have a stack here. Okay. Got my macro again. Hopefully this is all still correct. So my thinking is basically I have a stack of nodes. That sort of helps me keep track of the traversed path. That got me to the leaf node. And then if I have to split, basically I pop off the most recent parent. That tells me where the most recent parent came from. And then if I need to split, I push up to that recent parent. And then if I need to split that parent because it overflows, then I pop off the stack again. That'll give me the corresponding grandparent, the parent's parent. And hopefully that should be okay. So I have to do that whole, I've kind of haven't used this in a while, so I need to remember how to do this. So declare, oh, I have to hash included, of course. Dynamic array. And then declare dynamic array. I need a type, which will be btree node star. Hold a bunch of pointers, and the label will be called btree node I feel like the name's confusing. The node stack. It's a nice name, although maybe not specific enough. B node stack. Okay, so here's my thinking. When it's time to insert, go bang. Stack is equal to b node stack init given a capacity. Magic number time. Is this wrong? Should be pointer, should it? Okay, so I have a little stack, right? How nice. And the idea is, while current node is not the leaf, so we're going to put in all of the append b node stack, append the array, so the stack, and the value, which is of course the current node, I think, which is a pointer, right? So we append the current node, which is a parent, because it's not a leaf, right? It's a parent. We append that guy to the stack. Hopefully that's correct. And then if the current node num keys is greater than max keys, we have to split, we have to get the parent by popping off the stack, and then we have to push off the parent, push the median up to the parent, and then maybe I should say, and then set the current node to be equal to the parent. And so this should be a while loop as well. While the current node num keys, I don't know why I double equaled that. While the current node number of keys is greater than the max keys, split, get the parent, push the median up to the parent, and then set this one. And that way we can check if the parent also exceeded the number of keys, I think. This is a bit of a chunky function, actually. I should split this a bit more, but anyway. So while the current node number of keys is greater than the number of keys, how do I want to do this? Would it be better to malloc the key separately? Like, and pass in an actual key struct here? That way, because when I do this pushing up the key up to the parent, that's already a key struct, not an integer, that's a key. So maybe it's better if I'm giving a key to this as opposed to an integer. And then the mallocing happens somewhere else. Void btree key init given the integer. It's not really void, is it? So this is B tree key star, do all this, and then return new key. Okay, so get rid of all this. Instead of giving a key, we give a B tree key star, new key. And I'll just say int key is equal to new key value. That way I don't get errors. Okay, so get rid of all of that. So when I call that function, wherever I called it, I would say B tree key init given the key, and then B tree key star new key is equal to this guy, and then give this guy over here. That way I'm giving a new key, the actual struct as opposed to an integer, and I think that's better. So while this current node num keys is bigger than the maximum keys, right? While that's the case, I'm going to split. I've been avoiding the splitting, but I think I have the structures now, like the ideas now. So I'm able to insert into a node. I'm able to insert a key into a node. I'm able to create keys. So void split node. B tree node split. Given what, a node? That's it, right? Surely. Maybe a parent as well, actually. B tree node parent. Is that a good idea? So step 1, we need to determine how many nodes there have to be in the left split and the right split. So if there are 5 nodes, if it overflows at 5, 1, 2, 3, 4, 5. If it overflows at 5, that means n is equal to 4, the hyperparameter is equal to 4. That means the left child should get 4, and that should get 2, and the right child should get 2. So in this case, it's 4 divided by 2, tells me how many things in it. If it overflows at an even number, that means you have to be pushed up. In this case, this guy had to be pushed up. So n equals 5, so it overflows at 6. That means this side should get 2, and this side should get 3. So always the left children, the left guy should always get n divided by 2 with the integer division. Then the next guy will always be the median, and the rest will be the remaining. So that's a good pattern. So num keys on the left will always be max keys divided by 2. This will be an integer because this is this is integer division. Good. So for count less than num keys on the left. I shouldn't say num keys left, that makes it sound different. Keys on the left side kind of thing. And then plus count. So we're going to keep track of how many times this loop should run, and we're going to say okay, we're going to be very careful here. Node head, this is the key, B tree key star. Spell key without the capital. Left split, this is the left split, is equal to this guy. So just to clarify, I'll draw this properly. Here's the plan. We know how many nodes there should be on the left side, right? So let's use the overflow at 6 example. So 5 is good, n equals 5 is good, and then when we add that 6th node, that's when it spills. we know that these two guys is going to be the left split, and these three guys is going to be the right split, and this guy in the middle is going to be the guy that gets pushed up. So that means that U in here should be, we have a pointer pointing to the head, and for count equals 1, count equals 2, this will make us point to the median. This will make us point to the median. Okay, good. So I need a previous as well. So we're going to say previous is equal to the left split, I'll say median actually, equals the median, and median is equal to median. Next. So I should say the assumption is that node num keys is equal to max keys plus 1. If that's not holding, then you shouldn't be calling this function. So that's the assumption, that node of num keys is 1 more than the max keys. Okay, so we're going to move our pointers along until median points here, right? So for n equals 5, it's going to be 1 and then 2, right? We're going to move that along, and the previous is going to follow and be 1 behind, point over here. So previous should point to the very last node in the left split, is the idea. Yes. In the case where n equals 1, is that fine? Because max keys is 1, then left side is equal to 0. I guess splitting really shouldn't. Yeah, I guess yeah. If n equals 1, that means you have 1 key. As soon as you have 2 keys, you have to split. So I guess the left split is nothing. The right split has 1 thing in it, and the top thing, the median, is the top. Okay, yeah, I guess it works. Previous is okay. So yes, I think I do have to be careful in the case that previous is null, but maybe I'll get away with it. We'll see. Whoops. So we have this and this. So I think what I can do is say B tree node left split. I haven't used that, right? Split. I haven't used that, right? Okay, good. Left split is equal to malloc size of B tree node and the idea is left split head is going to equal the actual head, this guy, right? B tree node right split, same kind of plan, except the right split head is going to be equal to the median next. And then by math, I'm pretty sure I can safely say that median will not be null. Because even in the case where count is equal to 0, because max keys is 1, like there's no iteration. So sorry, this is 0, sorry. In the case where max keys is 1 and this is 0, like median will point to the head. You know, I'm pretty sure median will always be non-null. And so right split head is equal to that. Actually, I don't actually want this to be a new malloc. I actually want this to be node. Because I said before, right, the original node should take in the right split, should be replaced by the right split because of the way the edges are pointing. I think I said that. I hope I said that. Because, for example, this yellow edge pointing to the overflowing child will eventually point to the right split because it's the numbers smaller than 71. So the right child, sorry, the original child that is smaller than 71 becomes the right split that is now smaller than 71. So that's why I don't want to create a brand new node for the right split. I only want to create I want to use the original node given here to make the right split. So this is the left split and this is the right split. Left node head is this one, right node head is this one. Right, left split and right split. And then I think it's fair game to say, God, B tree node insert, given the node, which is the parent node, and the new key, which I think is the median. This is why I rewrote this to take in a key instead of an integer, because I think I can very swiftly go like that. And what I should do as well, actually, I forgot to do this. What I should do is say previous next is equal to null. The previous was originally pointing to the median, but I want to disconnect this. I want to get rid of this so that this is just one. This is one. And when I do this, when I do B tree node insert with the median, its next should be the current key, is the idea, or be null if necessary. So its next should be redirected to the appropriate place in the parent node, and this guy is median.next, or median arrow next, isn't it? I've lost everything. Where am I? Yeah. Node head median next. So that's the right split. So left split we've done, right split we've done. Hopefully, the idea is hopefully this function should be everything I need. So the node, which is the current node, and the B node, which is the parent node. So I need to pop off the top. So I have to say stack indexed at, so stack data, sorry, indexed at stack size -1. And then also B node stack pop given the array. Sorry, I've renamed it badly in my macro. I shouldn't call it array, I should call it something else. That's fine. So yeah, the way I wrote popping is it's a void thing. It doesn't return the actual value. Maybe I should have done it like that, but it just gets rid of the last thing by reducing the size of the of the data. So size of the array. So I don't actually get the value out of it. So I have to just index in order to get it, and then where am I? And then call the pop function afterwards. Okay. So what I should do, actually, I need the value. So I should say B tree node parent is equal to this guy. Sorry, node. Then I should give the parent, just pop off the stack, and then say current node is equal to parent, for reasons I said before, because we want to be able to repeat this process if the parent overflows as a result. Now, I need to make sure I think the one thing I forgot to do was keep track of the sizes of everything. Didn't I? Where's B tree split? There it is. Okay, so the left split will always have n over 2 things, won't it? So this is all left. So this is all left. This is all these are all leaf nodes. So is leaf is equal to true. Head I've set greater than child is equal to null because it's a leaf node. Left split num keys is going to be equal to max keys over 2. Right? If there's a maximum of 5 keys, this one's going to have 2. And this one will have 3. The num keys were originally 5. You added 1 to make 6. So the node num keys is going to be equal to the max keys node num keys. So this is going to be the max keys plus 1 value because we overflowed. That's why we're calling this function. Minus left split num keys. That's me getting rid of the left split values, these ones. And then minus 1 because of getting rid of the median as well. So I think that's fair enough. Okay, node is leaf is true. I mean, it should already be set to true, but just in case. And they should already be null, but just in case. So head should be set. It is. Is leaf is set. Num keys is set. And previous is null. So all of this is for the left split, and all of this is for the right split. And the median is being pushed up to the top. Hopefully that's correct. I don't know. Should I try it? Alright, let's see what we can break, shall we? So let's try and insert 9, 15, 26, 2, 14, 103, 21, 47, 31, and 999. Okay. So, I mean, the thing is, even I don't really know what this is meant to look like. I think they're arbitrary visualizers. Max degree. Wait, what's a degree? Is degree the number of kids? If degree is the number of kids, then max keys is 4, which means max degree is 5. Now what? How do I... Okay. So we insert a 9, and then I'll do them like this. A 9, and then a 15, and then a 26, and then a 2, and then a 14. So we should, yup, there we go, because max degree was 5. So after 4 kids, had to do that splitting and pushing. 14, and then 103. Wow. 103, then 21. Then 47. Wow. 3 kids now. 47, then 31. And then 999. So big. Okay, we'll do one more. Nah, that's fine actually. Okay, let's just see how we go. There was a bit of pushing up there, you know. Maybe I'll do one more just to... Let me just check one thing. Did I use the... It's hard to see what's going on. Did I use the greater than link if things were too small? Yeah, I did. Okay. While it's not a leaf, move down. Oh, did I append? I didn't. Okay. And then I pop at the end, don't I? And then I should say B node stack free, shouldn't I? Or risk bad things happening. Does this just free? I forget, how does my free function work in here? I free the data and I free the arrays, which means I free not much. Okay, I don't actually free the items inside, so you'd have to deal with that. Which isn't that bad, you just iterate through and do it, so it's not too bad. But okay, void tree node free. Okay, so all this happens, and then hopefully nothing bad happens. Now, how do I show how do I want to traverse? How should I traverse the tree? Should I print the entire node and then travel? Bang, bang, bang. Print the node. Yeah, maybe I can have like a generation number. That's probably the easiest way of doing this. So print tree void print. I have a print node thing, don't I? So print the tree given the B tree node star. Nope, given the B tree star. Whoops. Int generation is equal to 0. That's like the 0th level root node. And then how do I do this? Tree root print node tree root okay, so I need to make this better. Did I call this function? I don't want to do this anymore. So we print this one. So we say printf gen %d tab maybe, given the generation number, and then do I want to put some indentation again? Could be good. Void print indent given a generation number. Just trying to think about how I did it with the regex like passing thing before. I think it was something like for int I equals 0, I less than generation plus plus I. Print f little space character, and then printf generate gen %d \n. No, not \n. Sorry. Maybe just a space should be fine. Generation. So then over here we can say print indent given the generation number. Yeah. Okay. And then print the tree in generation equals 0, print the node. Yep, so you're printing that root node. And the idea is you print everything in the node. And then sort of restart. Do a second iteration. But instead of printing, this time we're going to traverse print node B tree current is a key, right? Yeah, current child, that will point to the child node, and the generation should be generation +1. Then iterate along, and then print node given the nodes greater than child, And the generation should also be +1. What's this? Ah, the very last one. So this should be different. So this was so that the printing would be good. Go to current.next and then print the current key, the very last key, without printing the arrow. That's just for cosmetic purposes. But here we can just say from the start till the null, not including the null, print this next node, which is the child of the key, with a generation number that's bigger. Okay, I think I have a printing function now. That's good. So I do all this, and so I do all these inserts, and I say, please print the tree given the B tree. So I have to do the inclusion dynamic array. Oh, actually no, it's in the same directory, so I should be fine. Never mind. My mistake. Oh no. Okay, let me see. Who saw that one coming, huh? Please be the printing. Damn it. Is it all of the inserts or just one of them? Oh. So the very first root one is fine, which we checked already, so that's fair enough. And then the second one is also fine. So let me see what happens if I just go like that. So I'm assuming it's the pushing up. Oh, the printing also fails. Is it because of the null thing again? But I thought I had a, if it's not null, then, but maybe, yes, the node itself can be null, can't it? So if not node, then return. If there's no current, then return. Or node head is also null, then return, and then it should be okay after that, I think. That's what I imagine. Fair. Okay, so there's gen 0 is 915, which makes sense. Should I clear this and go again? Like if I go 9 and then 15, that's what it will look like. 9 and then 15. Just the gen 0, no nonsense. If I do 26, I'm assuming nothing bad will happen. I'm assuming the first issue will be when... I should put a colon after the generation thing. Otherwise it looks weird. So 0 to 15 to 26. If I have to insert 26, then naturally you'll get a 26. And I said the maximum is 4, right? So I think one more should be fine. So if I put 2, I should just get a 2 at the very start. So if I go like this and then go like this, I get that. I'm assuming where it goes wrong is when you put a 14 and then you have to do this pushy thing. Like that. I'm assuming mine blows up in its face. Okay, so there we go. So we'll make a breakpoint. I'm pretty confident that the first 4 is fine. You're just inserting into the root. There's no pushing. I'm assuming nothing bad happens. So I'll put a breakpoint there and also put a breakpoint. So it won't be here. Like here, where we check if it's bigger than the max number of keys. Did I increase this at all? Probably when I called tree node insert, right? I wonder if that's audible from from the microphone. Oh, what? Why didn't it break point there? Oh, I'm dumb. Of course it didn't. Hang on, let me get rid of that breakpoint. so breakpoint, get to there, and then jump in. Okay, so let's take a look at the state. So we have, the root. I have my debug console out. The root has a head, a next. The key is 2, which makes sense because before we added that 14, it was 2, 9, 15, 26. So it makes sense for the root, that one node, to have a key of 2. Then next we'll have a key of 9, which tracks. Then next we'll have a key of 15, which tracks. And next of that, we'll have a key of 26. And the next of that is null. So that looks pretty good. If the root is null, it is not null. We have stuff in there at this point. The current node is equal to that root. It's equal to the node, so the overarching structure, not just an individual key. I should close this. This is going to get really annoying if I keep this up. Okay. The stack I create to be that one. Hopefully the stack isn't what breaks, because that'll be really annoying. While current node is not a leaf. Now, because we only have one node at this point, remember, ignoring the for, just this one, this will be a leaf straight away, which is confirmed there. So this while loop should not run. Fantastic. We create a new key given the key. So new key, if I look at it, it has a key of 14, next is null, child is null, which makes sense. We then insert the node into, we insert the key into the node. So we can have a look at that, but I'm pretty sure this should be fine because it was working beforehand. So previous key is null, current key is the head, which is the key of 2, which makes sense. We go along while current key is a thing. So we're going to be inserting when we get to the 15. So this shouldn't happen. So this shouldn't happen. Bang, bang. Current key is now 9, so it still shouldn't happen. What are we inserting in? 14? Yeah. Then current key will be 15, I believe. So this is where we'll do the insertion. Current key is indeed bigger than the incoming key. So new key next is equal to current key. New key next should be equal to that 15. Very good. If the previous key is there, it is. Then the previous key next should be equal to the new key. Previous key next. Where am I? Previous key next should be equal to the new key. So I'll run that line. So then that means the next should be 14. So we're pretty confident that the 14 has been put in here. So again, we don't have this 14 up top yet. The 14 has been put in there. And there should be 5 keys in here. So break out. If not current key, because we got to the end, that shouldn't have happened. Node number of keys should be increased by 1. So node, which has 4 at the moment, when I run this line, should get to 5. And then we break out, we return. So we've done that. Current node is that node that we gave. So we can see the number of keys is equal to 5, which is bigger than the max keys, which I guess is not written here, but we know the max keys is 4. So while this is the case, this is where I'm assuming the error has happened. We try our best to get the parent, which should be null, right? Oh, that's probably why it broke. Okay, so the parent is null, so I'm assuming that's what's happened. We split. Yeah, okay, I didn't think about that. Where do I use the parent? Here. I did say something about the parent node needing to not necessarily having nodes in it, I think, when I did this. I could be wrong, but so when I do, yeah, so I see I access all this stuff and then, okay. So if the node is null, this means that we're creating a brand new node as well as a new key. So basically all this stuff in here needs to get created and put into here. I'm not actually going to copy and paste it, of course, but I just want to demonstrate what we're doing. If the node is equal to null, I've done all sorts of strange things, haven't I? Hang on. There you go. That's fine. So if the node is null, I haven't kept track of these things at all. That's a problem. I guess I don't have to do this as much, actually. Okay, so if the node is null, then I have to initialize a new, I have to btree node init maybe given a key as well, because like you wouldn't be initializing a node without a key, right? So I might as well say btree key first key, and basically all of this logic I think can be plopped into here. The first key. First next is null. The child's also null, I guess. Although it's not necessarily a leaf though, is it? Oh dear. Okay. Things have gotten a touch more complicated than I was hoping for. So where were we? So we were in the insert. While the current key, we get the parent, which is fairly null. There's no parent at this point. Btree node insert. While it's bigger than the number of keys is too many, give the parent. Okay, I think we have to be. I think this guy has to take responsibility. So when we use the parent node, we only use it down here. So we have to be a little bit more cautious regarding. Okay. If the parent node is not null, then I think this is going to be okay. Because I think everything's kind of been set up already so that it's going to work out. And maybe all this stuff I was doing over here. Hang on. How much stuff did I actually change? I kind of forgot what I just did. Let's get rid of all this for now. Okay, so I will just say assumption node is not null. This is the assumption we're making, because otherwise it's like, why would you pass an empty, like a null in here if you're trying to insert into this node, you know? So that's the assumption we're making. So when I call this function here and here, at this point, current node is definitely not null. That's fair game because we would have broken out when we hit a leaf node. So hopefully that shouldn't be null. Here though, we understand that parent node can be null. Parent node can be null. We've seen that. So we have to first check if parent node is not null, then do this. Otherwise, we have to be a bit more cautious. Specifically, we have to say parent node is equal to malloc size of btree node. right? Now, the parent node should already kind of be pointing, have its edges sort of organized correctly, I think. Like, I've tried to sort of rig this so that, you know, like I said, like this yellow edge will be pointing to the node that it's supposed to be pointing to already for the split. That's how I designed it. So if it's null though, then we have to be a bit more careful regarding parent node greater than child, I think is going to be equal to the right split. Because the idea is like, this is a brand new root. So when we split this guy in two, there's going to be a left split, right split. The right split is going to be the greater than link, and the left split this line should always be run, shouldn't it? This should always happen. And then after I do this, after I create the malloc, and after I create the parent node, and I say parent node greater than is the right split, then I think I can insert the median into the parent node, that key, that median key into the parent node. Now, just to double check something, the parent is now, the node is now not null, which is good, but the current key is also null. So this while loop shouldn't run, then what will happen? If not the current key, see, I think bad things will happen. Okay, so I will handle this case separately. If node head is null, then basically node head is equal to the new key next is equal to null. Node num key is equal to 1. And what else? Is leaf. I don't really know if it's false or true, right? So I can't really set that here. All I know is these three things. I think I can return after that. Fair? The head is the new key next is null. This is 1 and I return out. Otherwise, should be okay. I think. I forgot to do something. The parent node is leaf is false. The fact is it is a parent and it will be pointing to stuff, so it's not a leaf. B-tree node insert, parent node median. Okay, do we think I fixed it or what? If the parent node, then... So I think the better way of writing this is actually if it's not a parent node. If the parent node is null, then do this. Then do this at the end. And I think I might have to return the parent node because I need it, don't I? Like I have to return this value. So whenever I call it, I only call it once, which is good. The parent is equal to this guy. Because I have to do this. I have to say current node is equal to that parent. So yeah, and then, you know, if it is a brand spanking new parent, then this should be 1, which should not exceed the max keys, because your max key should not be smaller than 1. That'd be very weird. Okay, I'm a little bit more... That feels like it makes some sense. The writing isn't fantastic, but the overarching ideas, I think is okay. I do want to make this a separate function though. So like, B tree node init given a key. I think I was like kind of half writing this and then just thought against it. Basically, B tree node is equal to malloc size of B tree node, and then the node num keys will be 1 because it's a new thing. I don't know if it's a root or not. Sorry, I don't know if it's a leaf or not. But that's the responsibility of the caller, I guess. And then node head is equal to the key. The key's next is equal to null. Yeah. Okay. And then I just have to return the node. So here, instead of writing all of this, I think I can write tree. Firstly, I have to create the key, actually. So B tree key star new key is equal to B tree key init given the integer. So we make the key. Then we say tree root is equal to B tree node init given the new key. And what were the things I said I didn't need? Tree root is leaf is going to be true because this is like a brand, like this is the first thing ever. Is leaf is true, head has been set, num keys has been set as well, greater than child, we'll just set to null. And then the actual field. So this is a little bit cleaner because it's a bit more reusable. Okay, that should be fine, and then just return out. Anything else I wanted to fix? I can't remember now, but I think that was not too bad. Just, whoa. I forgot I did that. How much do we back this? Not much. Alright. What? Well, that's not good. What happened to the 9? So I lost it. It successfully didn't crash, but it also lost data. So yeah, it got the 4 things, and then when I tried to do my little split, it actually didn't even. Okay, so that kind of makes sense because what I think has happened is the root, which is meant to point to the left split, never got saved. Basically, it just has the right. It's still the root of the tree, of the overarching structure. It's still pointing to the original node here, which at this point is just this guy, because of the way I wrote it. So I need to actually be a bit more careful regarding. Okay, so it'll be something like the following. It'll be like when I insert, where's the insertion function? Here. When I insert parent is equal to this guy, right? Is this really dangerous? Actually, I've just realized, like, this never appended anything. Because this never appended anything because the current node was immediately a leaf. So this never appended, which means the size of this is just... the size of this guy is 0. Okay, I gotta be careful. Okay, here's what I'll do. I'll say stack size is strictly greater than 0, then do this. Otherwise, do null. And the idea is if the popped parent is equal to null, that is, we are at the very, very top of the stack kind of thing. Like there was no more parent to pop off, so we've just set it to null. I think that guarantees that we have a new root. So this node should equal the parent that we would have created in B-tree node split. I honestly think that it's fair game to even just return out of here. And then otherwise, if the parent wasn't null and it was something legitimate, then we will pop off the stack because we know that something was there, which will decrease the size by 1. Current node will equal to that parent. Yeah, okay. Let's just see what happens. So I think that was what was missing. Yeah, that looks pretty good. 15 and 26 is like that guy. 2 and 9 is that guy. And then gen 14. Okay, let's keep going. Very nice. Then if we do 103, we should have 3 guys in there. Yup, cool. 21. I did make the numbers kind of big, didn't I? Let me put one in here. Let's say 7. Right? That seems like it would make sense. 7 goes in here. Yeah. 31. Would go kind of here and cause it to bounce up. Yep. Well, here we go. So if I insert 31, 14 and 26 both got popped up. Very good. 279. Yeah. 15, 21. Good. And then 31, 103. Did I insert 103? Oh yeah, I did. Forgot about that. And then let's say we put like 1. Cool. Sweet. So yeah, 1 instead of 999. I just want to try and make this guy full as well, the top root. So you can see 1279 makes sense. Then 1521 as well, and also 31, 103, and then of course at the top you have 1426. Then if I put like a 10 in here, that should also put it in here. Split that, bring that up. Does that seem right? 1, 2, 9, 10. 1, 2, 9, 10, 15, 21, 31, 103. Good. And then 7, 14, 26. Okay. Let's do 22, 23, maybe? I'm getting a bit lazy, actually. Let's do, yeah, 22, 23, 24. Let's do 22, 23 first, actually. So we should have, yeah, basically those guys added to the end. So what did I say, 22, 23? Or yeah, 22 and 23. Cool. And that seems to match up. And then if I do 24, I'm just trying to get a second generation. That's why I'm spanning all this. Right, so we have, yeah, 24. So C-line. So we can see we've got 4 numbers up top, which kind of tracks, and then 2 numbers everywhere else. 1, 2, 9, 10, 15, 21, 23, 24, 31, 103. Which I think tracks. Yep. 7, 14, 22, 26, right? 7, yeah, cool. So then, if I do like, let's say, 8 and 12. 8, 9, 10, 11, 12, yeah, so that makes sense. And if I do 13, that should make this guy split up, which should bring it up top, and then make that guy split up as well, the root. So that splits, then this splits, and then this happens. So 13 was the last number. Yeah. Nice, we have the sort of new generation. So 0 is 14, then 7, 10. 7, 10 is the first gen. Then 1, 2, 8, 9, 12, 13. 1, 2, 8, 9. Oh, I lost stuff. No. Okay. So yeah, that extra, I thought something like this might happen where like I lose something somewhere because I didn't keep track of the pointers correctly. 14, 7, 10. I have the 1, 2, and the 8, 9, but the 12, 13, specifically the last one. I also wanted the 31 and the 1 and 3 as well. So that, to me, makes me think that it's that last, the greater than child. I think in my mind, I thought this line would be what kind of saved it, but maybe, okay, so in terms of the B tree node split, the split always happens on a leaf node, right? So that's why after just 2 generations, it works because the greater than child is being updated correctly. But in the case where it's a non-leaf child getting split, then something, no, that's not true. I call this function for non-leaf nodes as well, actually, so I'm a bit surprised. Wait, what was the field called again? Greater than child? It's greater than child link. Right. So this greater than child is only ever being updated if the parent node was null. But if the parent node was not null, like in here, the parent node was not null, right? It was, I forget exactly what it was, like it had stuff in it, and it was pointing to stuff, and because it's split, it now has to create a new, do you have to create a new edge? Oh, I've already forgotten what happened. So 7, 10, 0, 1, 0, 2, 0, 8, 0, 9. So when do I have to create a new edge? The 1, 2, 3, 4. Yeah, something to do with that field not being updated at all the correct places, but I don't actually know where to update them. Like, should this just be happening regardless? Surely not. Let me think about this again. So when we do a split like this, right? I really thought that the greater than would be pointing to something already. And so, like, what is it? 12 and 13, right? Those guys got inserted near the end, to be fair. And also the 31, 31 and 3 also. These guys also got lost. I don't know what's happening. 149, okay. We've got 15 minutes and stop. So if I have this, I know my brain, I'm tired now, but I really thought that, like, in the case where you have something like this, you have a bunch of edges already pointing to below children. When you do a split like this, where 72 gets pushed up, 60 and 71 have to go to one side, and, like, this is the parent that gets pushed up the stack, right? Let me just try to go through this. So greater than true. So the B tree insert, you current node is not a leaf. Current node here is not a leaf. Let me do it further. This guy's not a leaf. So we append it to the stack, and then current key equals current node head. Yeah. So then you iterate through until you find a key that is bigger than the incoming key. So 65 was the incoming key. We find the key in the node that is bigger than it. So we find this guy, and we traverse down its corresponding edge, which is the yellow edge. Like that, break out, and then in this case, the current key will become this guy, which is a leaf, so this will terminate. We create the new key, which is 65, and we insert it into the current node, which is this child here. Then we'll have a split. Maybe the issue is I need an extra parent. Like, let's say this guy over here is like 85 or something. and so points down here, you know, and then there's also another one that points over here. So then there's two things on the stack. There's 85 and then this guy on the stack, and then we find our current leaf. We add to the current leaf, and then it exceeds the maximum keys. So parent equals either stack. If the stack size is greater than 0, then we get the most recent. So the parent is that guy originally. We split the nodes as necessary, like this, bang bang. I'll just add the 85 in here as well. We add the what am I to? B tree key in it. I've lost everything. Yeah, no, yeah. We get the parent, which will be this guy, and we say parent equals B tree node split. So we split this guy, make the 40, make the 65. So this is the left split, this is the right split. Left split, the median key, child should become the left split, and the right split, I think, can just kind of chill out a little bit. Current key equals current key next. Oh, so we do that. Then current node equals parent, we pop up the stack, current node equals parent, the current node is now here. And we check, are you greater than the max keys you are? So we get the next parent, which is you. We split it here, so the 72 gets pushed up. Oh, but what happens? Oh, maybe that's what's happened. So the pink edge, when the median gets pushed up like this, what do I do to the median's child is the left split, right? So the median, this median, which was 72, its child, its pink edge will now point to the left split, which is the 60, 71. So the pink edge, which originally belonged to the 72, now needs to become the greater than edge of the 60, 71. I don't know if that made any sense, but I think I understand what happened. So I forgot who owned what, and that was the problem. So okay, here we go. So when I do median child equals left split, I have to say left split, I think greater than child is equal to the median child, I think. And what about, I lost both greater thans. I was surprised about that because there was that, I shouldn't have skipped back, I shouldn't have done all that. What am I up to? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So I need 7, 31, 1, 10. Is that right? 7, 30, 7, 31. 7, 31, 1, and 10. 23, 24, 8, 12, and 13. Right. So let's take observation here. What happens is the 13 will go here, which means the 10 will get pushed up to here. The 10 originally has no children, but it will now be pointing to the 0, 8, 0, 9, like 8, 9 child, which I think I do because median child becomes the left split. And the 14, right, the median next. Node split. Yeah, no, that's fine. The 14 originally points to here. Will now point to these two. That's why I said, right, the node, the original node that was splitting, kind of takes on the identity of the right split. So 14 originally points to the entire node, now points to that right split. That's actually fine. So I'm not actually doing that. That was the reason I did it like that. So bang, that's fine. This one points there. But in the case where this now overfills, the 14 is now going to get pushed up. Now the 14 originally pointed over here. The 14 originally pointed over here when I push it up because the 13 will be here, right? 13 will get inserted over here. No, yeah, 13 will be here. 13 will be here, sorry. Then the 10 will get pushed up to here. And the 14 will get pushed up above. And the 14 gets pushed up. I think the 14 will be told to point to the left split, right? Which will be the 7 and the 10 that get pushed up. And the greater than edge should be told to be pointed to the 20, 26 split. But see, that 26 should still be pointing to that rightmost. Sorry, the greater than over here should still be pointing over here. So I think maybe I just didn't bookkeep well enough and then something happened and got lost. But I'm a bit surprised because it still managed to figure out the 14 thing. It knew the 14 should get pushed up, and it knew that this is Gen 1, 7, 10. And it knew the Gen 2 was 20, 26. So it knew the Gen, sorry, it knew this Gen 1 here was 20, 26. So it knew this Gen 1 was 20, 26. Why couldn't it find 31, 103? I don't understand why this Gen 2 was lost, the 8, 9, 12, 13 was lost. I don't understand that, but I know I feel like I missed something else. I don't know. Left split greater than child. The left split greater than child will be whatever the median was pointing to originally, over here. And then the median child in turn will point to the left split. When it gets pushed up, will point to the left split. If there is no parent node, we malloc a parent node. The greater than child. That's what's happening here, right? When there's no parent node. So the parent node, we malloc the new node up top. The greater than child will be the node. What? Wait, something? Yeah, we're splitting we're splitting this entire node, and we're saying that the right split is, we're going to keep the right split as the node. So the greater than child is going to be that node. Head is just null. Is leave is false. B tree node, insert the parent node, insert this median. Oh, it's at the window. Okay, so the left split greater than child. Left split greater than child should point to whatever the push up median was originally pointing to. I think at least that should save one of the. Yeah, so I got the 12, 13 now, which is great. So just to clarify, I got the 13. Right, that I got the Gen 2, and Gen 2. But yeah, like I said, like this Gen 2 is still missing, the 31, 103. I'm not understanding why it's missing though, because I can see why the 12, 13 was missing. That's why I had that extra line. But I don't get why this line had that. But I don't get why, because when the 20, like, okay, when I split, let me go back one. When I split this guy, because the 10 got pushed out, when I split this guy, this dude, your greater than was originally pointing to 31, 103, right? I'm pretty confident that because before I put in this 13, everything was fine. Gen 1, Gen 1, Gen 1, Gen 1, Gen 1, 2, 3, 4, 5, right? That fifth kid is there. So I'm pretty sure that the greater than is pointing to the correct thing. When I insert the 13, what's happening? The 14 gets pushed up, the split happens, but my point is the right split is the same as the original node. Unless it's not like B tree, insert, B tree, split. Oh, whoa, why did I set this to null? Okay, I see what's happened. So I've assumed that node, I've forgotten that node might not be a parent, and I've set this to be true. I think I did this for safety reasons. I should not have done that. That was really bad. This should be like this. I actually overzealously tried to be safe, and I actually had the exact opposite effect. There we go. That was actually quite dumb of me. Yes, so node can be a leaf node or a parent node. We don't know which one it is. We are just splitting. Okay. There's probably more bugs. I'm sure I've made other mistakes, but for now, we'll leave it at that. We'll check leaks actually. How's my freeing function? Leaks at exit. Fair enough. Malloc in B node stack init. Oh no. Okay. Cool. There's 4 leaks. It's not so bad. So the nodes. Oh, I didn't free that correctly, do I? Didn't I call free though? I'm confused. 96 bytes. Node stack init because there's 10 things and there's. Oh man. I'm confused though. Didn't I only do this once? I only called this function once. How can there be 2 leaks? There's U, which comes from line 309. Oh no, wait, but it's within this function, so it can happen multiple times. Fair enough, yeah. I'm very much confuzzled. What is happening? Is it always that? B node stack. B node stack, B node stack. It's that one twice. So I've actually managed to free stuff quite well in here. I just, for some reason, messed up the actual... Ah, because of this. Isn't it? It's because of that. Because I didn't want to... What? If I just get rid of this return, I don't think I need to worry too much, right? Because I don't think... The early exit was like because I was paranoid, but I don't think anything bad will happen because if the pop parent is null, that is we've created a new root because we've managed to like split and bubble all the way back up to the top. If we've created a new root, we set the tree root to be this new parent because that's the new root. Then what happens? We pop off the stack. Is this dangerous? Yes, because the size is already 0. Current node equals parent. Yeah, but I mean, the size will go to -1, which of course is a bit dodgy, but then the current node will be set to parent, and that parent will have a number of keys of 1, which will not exceed the max keys for sure. So you'll definitely break out of it, and then you free it straight away. So I think it's okay if you don't return. It's a bit hacky, but it's not too bad. So that's fine. And then if I do this, hopefully, yeah, okay, cool. I was returning early so that this freeing wasn't being called. That's all it was. Okay, that should be that's a good start. That's not bad. There might be more logical problems in terms of if I do more and more splitting, maybe something else will break. But I think it feels relatively logical. There was one logic issue where what was it, line 133 or something, right? This not having this line, fair enough that caused problems. I can see that because when you bubble up, you need to point to the parent that you came from, which I did do, but that means that who you were originally pointing to is now lost unless, in this case, the left split points to that child that you were pointing to when you bubbled up, before you bubbled up. So that's fair enough. Okay. Very good. All right. So we are continuing on with our B tree development. But yesterday I finished by saying, oh, we'll do deletion operation next. But I lied a little bit, and it turns out there's something else I want to do with the insertion. I believe there is a bit of an obvious optimization I can do, which I realized after I finished recording yesterday, because when I insert, what I've done so far, I've changed a lot of the code, a good chunk of the code, so I'll explain all that. But basically, the general gist was, when you insert, when we do all this whole thing, we have the stack. Oh, I missed. Wait, what? Where's the stack? Huh? Oh, wait, sorry. B-tree insert versus B-tree node insert. Sorry, I was looking at the wrong one. B-tree insert. When you insert in here, you have the stack, which at the moment holds nodes, right? And the whole point of the stack is to keep track of the order of traversal, keeping track of the parents that we traverse through before we get to the leaf node we want to get to. And that's kind of how this whole thing works. Now, what I realized is, what did I realize? This might take me a minute to remember what I was doing. So you figure out the parent, and then you get to the leaf, and you insert the new key into that leaf node, right? Now, when you do this, when you do exceed the max number of keys, right? The idea is you figure out the most recent parent by backtracking through the stack. You figure out the most recent parent, and we do the splitting thing. Now, at the moment, when you do this split, what has to happen? Okay, let me think about this for a while. Hang on. I might have to cut this out, but I just have to remember what I was thinking about. So you have a parent. Yes. Okay. When you have to split the node and put the middle guy back to the parent, you have to insert that middle guy into the parent somewhere, right? And the way I do this now is I call the B-tree node insert function. This might be a little bit different actually, but I'm pretty sure this was what happened last time. We do the whole left split, right split thing, and we take the median and we insert it into the parent node. And this particular function involves iterating through all the nodes, figuring out, which position is most appropriate for this new key so that we keep the sorted order, right? That's what this function is for. It's a full iteration. But this is a redundant thing, I believe. And this is where I have to slow down because I have to make sure this makes sense. Way back here, when we are building up the stack, right? We already do this kind of check where we check if the key is the parent key in the parent is bigger than the incoming key. So I think if I do an example, I think it'll make sense, hopefully. Let's take the 65, right? So we're inserting 65 into this structure. The idea is 65 isn't there yet, and we're going to insert 65. So we flow through the parents and stuff, blah, blah, blah. We find the leaf node. But specifically, it's this key that we traverse through in order to get to the leaf node, right? It's this key we traverse through in the parent. So when we insert 65 and we see things overflow, we know that, the 60 in this case has to be pushed back to the parent, right? The median guy has to be pushed up to the parent. We do the split down the middle, and the median has to be pushed up to the parent. Now, like I said, when the 60 gets inserted into the parent, at the moment, we loop through the entire of this parent node to figure out where the 60 should go, right? we loop through the parent node to figure out where the 60 should go. But we already know that the 60 should go before the 71, because that's the key we traverse down to get to this child node, to this leaf node. We know the 71 is sort of the next biggest key, because like this set of nodes, this set of keys, sorry, are all going to be smaller than the 71. So the 60 is going to be should be right before the 71. If I take another example, let's say one from the middle. Let's say we were inserting, let's say there was another sort of node over here for this blue edge, which had a few keys in it. And then let's say we're inserting 70. Oh, I've made this bad. Let's say we're adding like 72.1 or something. I'm not doing floats in reality, but let's just for the example, right? 72.1. When I figure out my my leaf, I know I have to traverse through this blue edge, which, by the way I've designed it, is associated with the 73 key, right? So I'll just get rid of 71 circle over here. Like, I know that I've had to traverse through the 73 key in order to get to this child, right? So if I end up overflowing and I have to take whatever this is, I know that this guy in the middle, this median, is going to be bigger than 72 and smaller than 73. I know that because I traversed through this edge, which is for the keys that are between 72 and 73, right? So I shouldn't have to re-loop through this entire thing to find the 73 and insert the median into the middle there. I shouldn't have to do that because I already know it. I just have to, so before my stack, hopefully that made sense, before my stack has been keeping track of the parent nodes. But my realization is I can actually keep track of the parent keys that you're traversing through. And if you do it like that, then I don't have to do that second loop. I don't have to call the particular function, insert, key insert, whatever it was, node insert, this one, where you have to re-loop through everything. And check, where's the best place to put it. We already know where the best place to put it is when we traverse down the tree. So hopefully that made sense. That's the optimization. I don't have to do that many. I can get rid of one of my loops through the node, through the parent node, if I keep track of what key I traverse through rather than what node I traverse through. So that's like the overarching idea. Now, there was one problem with this, and that is, instead of one of these sort of, yellow, pink, blue, or green edges, if I traverse through the orange, right, through this orange edge, remember that the way I designed it yesterday, the orange edge is not associated with a key. The orange edge is associated with the overall node. It's the greater than edge, right? So, considering that I want to make it a stack of keys instead of a stack of nodes, what do I do if I traverse through this edge? There's no key to push onto the stack anymore, right? It's a node. So, if I wasn't using C, if I was using like Java or something, maybe I could make nodes and keys some kind of interface, like I was some sort of share some kind of parent class, and then maybe I could get away with it. In C though, I don't know if I can get away with stuff like that. So I could try some void star stuff, but I don't think it's necessary. What I've decided to do is create a what I call a tail key, a dummy tail key. So we have 71. Hang on, I got my pen. Hang on. So in this case we have 71 to 72 to 73 to 74, and instead of just ending it there and making the next thing null, I have a dummy key which I'm just going to say is 0, and that guy points to null, right? Now, how do I recognize the dummy key? I've added a field in the keys called isTail. It's a Boolean field, isTail, right? So this guy, for these guys over here, the isTail is going to be false. Only for this 0 guy over here, isTail is going to be true. So that's why, without having to go all the way to null, I can recognize if we're kind of at the end, quote unquote, the end of the linked list. Right, and the this isTail key is going to link to the child. It's basically going to hold this orange edge and link to the child node which has keys that are bigger than everyone in here, is the idea. So it's a dummy because it's not a real key. And I'm not going to be counting it towards my key count in my structure. But it's there so that instead of having a greater than link edge that is associated with the node, I have the greater than edge associated with another key, so that when I do this stack idea, I can just put keys in the stack. So it's like an extra key that I have to put in the node, so it's a little bit extra space, but it means that I don't have to do this extra loop when I'm inserting a key into a parent node. So what I've done so far, and these are the changes I've made. What I've done so far is I've made the is tail, and I got rid of the greater than field in the B tree node. So basically, wherever there was a greater than, then I might have commented them out. Yeah. So for example, whenever I've had to set the greater than child to null, I've just created a tail instead, giving the key value as 0, but then setting the thing to true, the is tail field to true. So I've added the is tail parameter to this function, the key initialization function. So that way, if you ever want to create a tail key, you can do it like that, setting that to true. So it doesn't really matter what you set the key value to. The is tail part is the important part. Yeah, so a bunch of stuff over here, like instead of saying left split greater than child is equal to the median child, that's one of those things, that's one of the changes that's one of the lines that were really important. Instead of saying that though, I say the left split tail, that dummy tail, its child is going to be the median child. So basically the greater than child field is replaced by the tail's child field. And so there's a bunch of changes I've made to adjust to suit the new thing. The B tree node init function, when I create a node for the first time, now inherently creates a tail, and it links. So I'll explain properly. It gives enough space for the node, of course. It sets the number of keys to 1 because there always has to be at least one key in the node for sure. The head will naturally be that key that we created, or that key that is given. Sorry. But now the extra thing is there's going to be a tail node that we also produce, and the key, the head, the keys next is going to be the node's tail, which is this key, this tail key we created, and then we return the node. So yeah, like I said, number of keys is set to 1, not 2. There are 2 keys technically because the tail is a key, but I'm not counting it because it's not a real key. It's just a way of holding that greater than child, using a key instead of using the node itself. There's a bunch of other things. I know, like in loops, yeah. This was a loop that said basically while the current key, this used to say while current key. So while the current key is not null is what this used to say. Now I'm making sure that the current key is not the tail, because essentially in certain contexts, the tail is acting as the null. It's like, it's the object that's not a real key. The first object that's not a real key in the list. So while the current key is not a tail, then we know that we are at an actual key. So we can do whatever this is. So yeah. So now what I want to try do is what I have to do now is I have to adjust the stack to, instead of holding nodes, it should hold keys. Be key stack. So that should give me some errors. Good. And then we will try adjust them as so. So B key stack equals key stack. Oh, I know I did, after all these changes, I did check all my, I did check this test case again. It seemed to be okay. There were some errors that I had to fix up, but yeah, it seems to be working now. But yeah, let me keep going. Wait, there's no more errors after that? There should be. Stack, B key stack, like B node stack should not exist anymore. So while current node, so I don't think I append here. I have to first find where the key is. So if the current key is greater than this incoming key, current node is equal to the current key child current node is equal to the current key child, and then current, I have to add this is where I have to add to the stack. So B key stack append, given the stack, I have to add the current key. That will tell me what key I traverse through in order to get to the child. Yes, I think this makes sense. And then blah, blah, blah. If we got through up and we got to the tail, this is another way, this is another time where I had to use the tail. If we got to the tail and we didn't, yeah, if we terminated out of the while loop because we got to the tail and not because we broke out, then that means the current node current key is equal to this current key, right? Because remember, for when it is the tail, this current key is the greater than key, basically. The greater than holds the greater than child. And I should append this guy instead. Yes, I think this is right. So either this will happen, we'll break out, and this won't happen, or this will never happen. The while loop will terminate, and then this will happen instead. So either this or this will run for a particular key, for a particular node, sorry. Then the while loop will happen over and over again until we reach the current node, until we reach the leaf. And now, this is very similar, except it's B tree key. B tree key. We have to split based on a key parent, not a, and this should be called a parent key, not a parent node. So yeah, this tells us what key, the smallest key that is bigger than the incoming thing. Yes, because any key in this particular node will be smaller than the parent key for sure, because that parent always links to a node that holds keys that are smaller than the parent. That's the whole property of these B trees. So blah 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 blah. We figure out our left split. We figure out our right split, which is just the original node, right? By design, we did that like that. And then we figure out, so the median child, because the median's child is the sort of child of this particular node that we've passed in. The median's child, the left split's tail child, yeah, that makes sense, like that's fine. And then instead of parent node, okay, so if there's no parent key, then I think ooh, wait, is this gonna make things hard? I didn't think about this part. So the B tree node, we return a B tree node because we might be creating a new root as a result of all this. Maybe it works if I pass in the B tree itself. Okay, this might take some thinking. If there was no parent key because like we basically have reached the top of the root, the top of the tree, sorry, and we have to create a new root. That's what this whole thing was about. If there's no parent key, then we definitely have to create a new node. That's what this root is for. Parent node. Okay, so let me say new root, because I think that's what this is going to be. The new root, which is a B tree node star. The new root is going to be that guy. The new root tail child is equal to node. Does that make sense? Yes, because the right split, basically. The node represents the right split at this point, and basically the tail child, which is the greater than, is going to hold that right split because it's in, the new node, which has one person in it, so that's going to have two edges. The right split is going to go to the tail, And what about the head? Does the median, well, the median already points, the median child already points to the left split, so this should be fine. And the new root is leaf is equal to false. I have a new root, so I have to associate that with the tree. Okay, here's what we're gonna do. I'm gonna, instead of doing it the way I've done it, I'm gonna pass in B tree itself. And I'm gonna say tree root is equal to the new root. I think this will be okay. And maybe I'll make this whole thing void, because the whole point of returning that was so that I could update the root if necessary. So if I get rid of all that, otherwise I'm not going to call this function, because that function is for if you're going to loop through the entire thing to figure out where to put the median. Instead, I know that the median next should be equal to the parent key, right? And then I need the thing before the parent. I need the one before the parent key to point on her. Okay, this has got complicated. This is where having a double linked list maybe is helpful. Do you want a previous key? Yeah, because I need to link, like I need to link the median to the key, but I also need to link the previous key to the median as well, so that it's a cohesive linked list. Oh dear. But if I add a previous thing, that's gonna add that's gonna add some complexity to the code. Like everywhere. Whenever I say next, basically I have to make sure I update the thing, I think. New key next is equal to... What is it about? I forgot why I wrote this. Is this the same thing as... B tree node insert? Do I call this function anymore? One, no, there, I call it there. When you get to the child, so yeah, here you might have to loop through, because you loop through at that point. But this one should have a head though. So I don't have to do this anymore. Because the reason I had this, if same was the case, like in the other call, in the other function called this one, if the parent node didn't have a head yet because I done it like empty, so it was a bit dodgy. So I think now I'm doing like I don't anything. Bottom line, I don't anything. The assumption is that node is not null, and node head is not null. Is what the assumption looks now. I think I'll be right. We'll see. But yeah, okay, that's fine. So then we go to next. So I shouldn't, because I shouldn't need to create a previous key, but I should find a key for now. Previous key next is equal to new key. Should I be like new key previous is equal to the previous key? Else node head is equal to new key. Did I use the new key previous is equal to null? So thank you. This is fine. Okay, previous key to new key previous is equal to previous key. New key next is the current key previous is equal to new key. So I just take a step back and recognize what I've done. This is when you try to insert a key into a particular node, keeping it in the same order. So we first go through all the nodes looking for a node that is a key that is bigger. So if we found one that's bigger, if there is a previous key that is not the head, then if previous key is there, then previous key next is equal to new key previous is equal to previous key. Did I set the new key down? So current key previous is equal to new key. Okay, good. So if that all happens and otherwise we move along, if we get to tail, then that means that the new key should be the tail, that current key, yeah, should be new key. Okay, that looks good. Median equals next, we find we're iterating along. Previous next equals left, so that means that left splits tail previous should equal previous. Does that seem right? So this is for the splitting. We create the left split, we set its things as necessary. Shouldn't I be able to say, no, that's fine. You know the number of keys, previous next, so what's previous? So this is finding the median, previous is right before median, so previous next is going to be left split tail, which means left, that's fine. And then node head equals median head. Yes, it's the right split, so this one, that's fine. Node number of keys is equal to that, that's fine. Left split tail child, median child, left split. We talked about that before, I backed that, I think. This should be fine, I think. Did I use it? Yes, I did. I set the key next to be the node tail, and the node tail previous to be the key. Okay, that's fine. So splitting. And then if there's no parent key, then do all that. Otherwise, median next should be equal to the parent key, which means the parent key previous should be equal to the median next. But I gotta be a little bit careful because I need to use, so previous parent key previous next is equal to the median. So whatever was behind the parent key, its next should now point to the median instead. Median should point to the parent key. Median's previous should equal to this guy. Parent key is still pointing there. Still pointing that guy, so now it should point over here. So median, how many links do I have to edit? Let me just clarify. So what I have basically is 1, 2, and then this new median is coming through here. So I have link number 1, link number 2. So what I have to do is reroute this red to point over here. So I'll dot them. So this red is pointing over here, and this blue is pointing over here, right? The previous is the next and the previous. I need that red to now point like this and up, and I need the blues to be redirected like this. So this is the dot is what it originally looks like, and it has to change to this. So medians next should be equal to the parent key. That should be fine. Median previous should equal to the parent key previous. So we've handled do it in green. We've handled the median sort of links. Good. Median previous. This one next. Of course, this guy has a next and this guy has a previous, but those two aren't going to change. That's fine. Now after we've done those two, which I think I've rewritten it so it does it like that. Yep. Now the parent's previous should be the median. Parent key previous should be the median, not the median next. I don't know why I wrote that. Parent key's previous should be the median. And the parent key's previous next should be the median. Yeah, so I should do this one first, because if I do this one first, then this guy will be the median. And then it will point to itself or something. So parent key previous is next. So parent key's previous is next. So this guy should point to median, which is good. So we've done that. And then the parent key's previous itself should also point to. I think they'll go in the right order, because the median basically is pointing completely in the wrong place. So we can edit its pointers no problem. Median next, median previous. Then the previous is next, and then the parent's previous. Okay, I think that made sense. Remember that the parent is this guy for sure, because the parent is always going to be bigger than our median. That's what the whole point of this optimization is. Okay, I have errors apparently. I don't know where else I would have them. I kind of forgot what I was doing, to be honest. What's this? Oh, of course, nothing returns. So I believe the idea is I don't have to do this anymore, because I'm editing the root in place if necessary. So I don't need to do this. I can give this the tree, because I remember giving the tree to this function, so I can, as in, this function signature has the tree, so I knew I could pass the tree in here, no problem. We do this, we pop it off the stack, and then current node equals parent. Do I set the number of keys correctly everywhere? That's important. Here I know I set the keys to 1, so that's good. Here I set the keys to 1, and then otherwise ooh, wait, yeah. I've just realized when you push, I don't update the node, do I? Because this function, despite having the extra loop, does increase the node's number of keys. I'm not doing that anymore, am I? Because I'm only working with the key. How intriguing. There's a couple of ways we can do this. I could try to add more bookkeeping and keep track of what node a key is currently in, but that feels annoying. The other option is to actually have both stacks. have a key stack and a parent stack, node stack. Sorry, so that every time you pop off the stack, you pop off both stacks, and so you get the key, so you can do this quickly, and also you have the parent, so you can update its fields as necessary. Is it particularly hard to add? Whoops, did not mean to do that. Like a field like this? I wonder. Because in my mind, when you make a key in it, you do all this. When you do this, you can immediately say key current node is equal to this node that we've created. The node tail is another key we create, so node tail current node is also equal to this node that we've created. Mildred's at the end. I have added a fair amount of bookkeeping that maybe I shouldn't have, but we'll see. When you insert a new key like this, naturally the new keys, is that wrong? Am I misunderstanding? Why is that not doing the IntelliSense? Okay. Did I put it underneath the return? There's no return. What? Why did it not? Am I tripping out? Like, I'm pretty sure I can just have that here, right? That was really weird. Anyway, so the new keys current node is equal to the node when we insert it in. When you split it, that'll also be another place where... Ooh, but that's annoying, isn't it? When you split a node, the keys themselves have been put into two different nodes. Half the keys have been put in the same node, but half the keys have been put into a brand new node. So that their current has to... Okay, I've changed my mind. I guess we'll have two separate stacks, which is very annoying. Okay. That's it, right? And then I did that. That's the... Yeah, okay. Okay. Wait, before we have two separate stacks, the fact is, I am... While the current node is not a leaf. Maybe I shouldn't have done this optimization. I just really thought it'd be easy. I didn't think it'd be this like annoying to be... do I really want to do this? Two stacks? What if I make a struct that's like key node pairs, and then I have a stack of that, and that way it's one stack that I handle, and it like lets me work with both guys, you know? Is that annoying? Is that like dumber than it should be? I just really don't have to deal with two stacks. Key node pairs. Pies. So like B tree key node pairs. And the idea is all you have is a B tree key and a B tree node. So we'll call it so for the stack, it's gonna have a bunch of these, and we're gonna call it the B tree. What did I call it before? The B tree KN stack. Wait, is that wrong? What did I do wrong? Identify a... Oh yeah, fair. Because I didn't do the type def. I spelled type def wrong. Okay, I think this is basically as good as it's gonna get. I don't know. What's wrong with that? Few two arguments in the function call. Is it? Ah, because I... No, what? Are we good? Okay. It's a B tree... What do I want to call it? KN stack, we'll call it. Keynode stack, we'll call it that. Why? Okay, I'm going to assume that it's just being annoying. And I'm going to... Oh, maybe because like I was cutting it out and it was getting confused. Expected a semicolon. What have I done now? What? Did I not put a semicolon at the end? I did not. Okay. Back down to here. Okay. Since I'm... Okay, I think I can just... So when I append all this, I think I can be like... When I choose to append, I think I can be like... what's the struct called again? B-tree key node pairs. B-tree key node pairs. I think I can do all this on the stack. So I can be like, my pair is equal to my key is equal to the current key, and my node is equal to the current node. And then I can be like, I'm going to append your address. And because you are going to stay in... Oh, wait, the scope will be violated, won't it? Yeah. Hold on. The scope's gonna get violated, right? Like as soon as when this if statement ends, this guy is gone. So don't tell me I have to malloc it, please. That'd be really annoying. Yeah, this address is gonna become stale. B-tree node key node pairs. The pair is with this and this. Am I really going to malloc this? Okay. B-tree node pair. Did I call it pairs? Hang on. Did I call it pairs with a... Oh, I did. Maybe I meant to save and put an S at the end. B-tree KN pair init given a B-tree key and a B-tree node. So we're gonna malloc size. This was meant to be like a super simple change. I didn't think this would be this annoying. Pair is equal to that. Star, of course. And then pair node equals n. Pair key equals k. And then return the pair. Okay. So then the idea is I'm going to say pair init and then give the node and give the current key. star. And then we're gonna give this guy, it's on the heap now, so it'll persist. The word pair now looks weird to me, I don't know why. Blah, 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 blah. And then if we get all the way to the end, and we didn't end up doing anything, then exact same thing. Cool. And then we make the new key, insert it in there. Parent key and B-tree node. Parent node. Yeah? Okay. So while this is a problem, while the current node has too many keys. This would have been the other problem. Yeah, so I definitely need to know what parent I'm up to, because I need to know. Wait, was that the problem I had before? Probably, right? I don't know. Anyway. Okay, so I need to first say B-tree node pair thingy parent is equal to this line. And then if parent, I should also say B-tree node parent node is equal to null. B-tree node parent key is equal to null. I said this wrong. Key. If the parent, the overall parent, I'll call it parent pair, if the parent pair is non-null, then parent node is equal to parent pair node, parent key is equal to parent pair key. So now I have to give both the parent key and the parent node. Fair game? I pop off the stack. Current node is equal to the parent. Ooh, okay, hang on. This is going to be a bit dodgy. I need the current node to equal to the new parent that I've created. Either like... I basically want it to equal to the parent node. But the parent node might be null, because if we have to create a brand new root. Okay, so I guess I do need to return the node. B-tree node star, like that. If no parent key, so here we return the new root, giving us the new parent. Otherwise, we return the parent key, the same parent key that we were using before. Why does this look weird? Oh, there's no space here. Okay, this is getting a bit annoying. Anyway, I think I can free the parent pair right before I pop. I'm not going to free the stuff inside of it because it's still existing. I just need to free the overarching structure. Current node equals the parent node, which will be equal to this guy. Either the same parent node that we passed in or the brand new root if we need that, and that way hopefully this will be fine. And the whole reason I did all of that was so that... Wait, no, not parent key, sorry. Return the parent node. Yes. The whole reason I did all of that was so that, you know, here, the number of keys is accurately set. It's set to 1. But here, parent node num keys should be incremented. Okay, I think I've just about managed to get it done. goodness. So basically, this operation, which was kind of like a quadratic type thing, because every time you had to insert into a parent, you had to loop through the parent. So it was like the number of parents times the size of the parent. Now it's basically you have to do one loop through the parent because no, not that one. You have to do one loop through the parent because you have to through the leaf node specifically. You do one leaf node. You have to loop through the leaf node once because that function does a loop. Then for every other one, it's kind of constant time-ish. So it's basically the number of parents you have to go through only. There's no multiply by the number of keys in each parent. That's like the optimization is the idea. Now, how much did I break? Oh, I broke a lot. Key stack. Oh, fair enough. I forgot to change all the. Okay, let me. B key stack. Anytime I did that, that has to change. So B tree. Oh, we're not gonna. B tree. KN stack. Append. Was it append function? KN stack append. B tree KN stack init. B tree KN stack append. There should be like a popping as well. Yeah. Oh, I didn't even change that one at all. B tree KN stack pop. Bang. Okay, so we're able to append it. We should be able to pop it off the stack. We should be able to do other things. Okay. I'm assuming that's probably the major issue. Okay, what else? Incompatible pointer. So the B tree key star. What have I done? Ah, of course, I forgot to change that. That's fair enough. So this should be B tree pair thing. Wait, why did I do this twice? Do I need this? Why is this here? Did I copy it? What did I do? I must have copied it up and then forgotten to delete this one. Oh, one more. Okay. Please don't be broken. Please don't be broken. No, it's completely broken. I've blown it up. What the flip? Huh? Just to clarify, if I don't print it, so it got to the printing part, so something happened. Oh. A trace trap. So when I tried to free it, something happened because the structure of it is just completely wrong. Put our bets in. What do we think I did wrong? Something about the previous, maybe? I feel like the previous was the most complicated thing I did in terms of like the additional bookkeeping. This was like annoying, but not that crazy. Oh no. Okay, let's try some stuff. Let's first begin by getting rid of everything. Let's only put 4 nodes in. 1, 2, 3, 4. So that we don't have to do any, because that will mean that we haven't pushed anything up yet. Okay, so if I try print that, we should be fine because there's no weird like we don't actually use the stack at all. Yeah, okay, so that's fine. Then I'm assuming when we do this, something bad happens. Oh, okay, fair enough. So zeros looks good, and then 2, 9, 15, 26 looks good because the 14 is what gets pushed up. I remember. Can I check one thing? Instead of saying while it's not tail, if I just say while next, and I get rid of this, I think that will also print the 0 for the tail. Oh, wait, what? Sorry, while current next. Ignore all that. Maybe I don't have to comment this out actually. I wanted to print the 0. There you go. Okay. So while current next is a thing, yeah. So it terminates when you get to when the current next is when you're up to the tail. It doesn't do the tail, so you print the tail. Okay, fine. So the zeros are there because that's the tail cue, the tail thing. So that looks okay. It looks pretty good. So the structure there looks okay. It would insert it into the bigger one. Yeah, that makes sense. 21, also the bigger one, I guess. Yup. Then 7 would put it into the smaller one, so in the first gen one. Yep. And then 31 would be in the bigger one, so this would cause the splitting again. Yeah, so 31 would be inserted here, so the 26 is the... Ooh. No, that's fine. So I thought for a second maybe because of the length change, because of the extra 0, I thought maybe the median was getting messed up, but I keep track of the num keys, right? Which is just these guys, 1, 2, 3, 4. And the fact is the splitting is happening at the correct time, so it shouldn't be that shouldn't be the problem. Let me just check this. So the 26 is what gets pushed up to the top. Yeah, that makes sense. I put a 1 in here, so the 1 should go to the left. Yeah, 1, 2, 7, 9, and then 10 should also go to the left, which will cause another split. So like I think 7 gets pushed to the top. There you go. Okay, so we found our minimum issue. What a shame. Okay, I guess, yeah, I'm not sure, it's weird because I feel like it's strange to me because it is, that was the last push, right? Let me print the tree right before this, just so I have it in the debug console. Hang on, let me try this one time. Okay, this should be good. So in the debug console, we see that, we have kind of what we had right before we insert this 10, right? This is everything before we insert the 10. And then we try to insert the 10, and I didn't put a breakpoint in the right place. That was dumb of me. Okay. So the B tree looks like this. The root looks like this. The head of the root is a 14, which makes sense. The previous is not null. That's already a bit of a dodgy thing. Okay. The next is 26. The previous is 14, which is good. The next is the 0. The previous is the 26. That's good. The next of this guy is null. Fantastic. Okay. So that's good. However, the what did I say? The root has a head of 14. Now I need to close all this stuff. The root has a key of 14, which makes sense. The head of the root is 14. But its previous is non-null, which does put me off. Because why is the root previous not null? I would assume it has something to do with the fact that I would have... It was 9. It would have been 2, 9, 14, 15... 1, 2, 3, 4, 5, right? It would have been 2, 9, 14, 15, 26, which means 14 was in the middle, and before it was a 9. So I'm assuming what I did was 14, its previous, is still the 9. So when I push something up to the top, I forgot to set its previous to the thing. Hang on. So when I do this split, if there's no parent key, then I initialize with this guy, which means the keys previous, here we go, the keys previous should be equal to null. So I don't know if that's the reason why there's a bug, but that's something I've forgotten, right? So the keys previous should be equal to null when you do this. In the else statement, so the split, right? If it's not parent key, you should have set that. If in the else statement, what happens? I did this pretty carefully though, didn't I? But I didn't really, because I made the assumption that the parent key has a previous. So I'm assuming this isn't null. I have to be very careful, actually. I wasn't very good at this. Because it's possible that the parent key is this guy, in which case there is no previous. The previous is null as well. So trying to access that previous is really dangerous. So the median next is this one. This is fine. All this is fine, because if this is null, that's fine. I have to say if parent key previous. If there exists a previous, then do this. Parent key previous is equal to median. Yeah, that's fine. Yeah, okay. That should be a little bit better now. Okay, so that was another issue, for sure. What else? Tree root greater than child is equal to null. I don't know why I'm reading a comment. That's not going to affect the thing. Okay, maybe we got lucky. Maybe that's the reason. Let's just... That looks pretty good, actually. Hang on, so this was before the change, and then when you insert a 10, it would be in the smaller section, so it would go to here, then the 7 would get pushed up. But the 7's gone, the 7's not there. Okay. When I put the 10 here, the 7 should be what gets pushed up to here, so they should be, say, 7, 14, 26, but it doesn't. Okay. So let's put a breakpoint here. I don't know why that's there. Let's run and debug this. Okay, allow. So we jump down. If the root is null, it is not null, so that shouldn't run. Let me have a look at this. So the tree looks like this with the root. Again, let me look at the debug console. So this is what the tree looks like at the moment. The root has a head of 14, and next should be null. So the previous is null, which is good. The next is 26. The next is 0 with the tail of true, and the next is null. Previous is 26, which is good, and the previous of this is 14, which is good, so that's fantastic. So all of that looks pretty good. Yeah, and then so the head then has a child, which should be this line. The head is 1, the previous is null, which is good. The next of this is 2 with the previous of 1, which is good. The next of this is 7 with a previous of 2, and the next of this is 9 with a previous of 7, and the next of this is 0 with a next of null and a previous of 9. Okay, so that seems pretty good. If I go root head next and then go child, so that should be root next child should be this guy. Head should be 15. Next, head is 15. Next is 21. Next is 0 with the next of null. Previous is 21. Previous is 15. Previous is... Oh, it's still not fully working. Okay. Previous is what? 14. Previous is 14. Previous is 14. When did I insert that 15? So it was 2. Because when you push something up to the top, this became the right split. So this is the left split, I think, and then this would be the right split or something. And so when that right split happens, the head of that right split's previous should be null as well. So when I split stuff, I've completely scrolled past it. Here we are. So the right split, the node head is median next. Node number of, so the node head, your previous should equal null. That's the only extra link you have to change. So the node head was before pointing to the median, right? Because median next, so it was pointing to the median. Now it's got to point to null. God, yeah. Node number of keys is fine. Left split tail child. When I split apart, the previous is next should point to tail, and the split tails. Okay, so that's fine. I back that. Then you get this guy. This right split should basically be absolutely fine, except this previous needs to point to null now instead of pointing to the previous. Number of keys is set correctly, I assume, because that's more like logical than it is to do with the code. And then this, the left split tail, so the n, so the greater than basically, its child, that greater than should point to what the median was pointing to before, which makes sense. And the median's child should be that left split. I'm a bit worried about something. I feel like I'm missing something. If there's no parent key and we're creating a new root, right? Oh no, I do set this. Okay, the tailed child is equal to the right split. Okay, good. I thought I forgot this for a second, but we're fine. Tree root is equal to new root. Okay. Okay. We want to check if that's what fixed it. No, right? Because what did I say? The 7 should get pushed up. When you put this, the 7 should get pushed up. Okay, so let's think about this. Let me try read through the code one more time, and then if not, I'll work through it with the debugger. So I'm making a bold assumption that when you insert the 10, it realizes that this guy is not, it is overflowing. And so it gives the 14 as a key and this overall node as the parent node. So this is the parent key, this is the parent node, is what I'm thinking. So in fact, I said I'll read through the code, but let's just run through it. Let's just see if that's correct. So we jump into here, we go bang, bang. While it's not a leaf, we figure out the leaf. Okay, we insert the, what was it, 10 or 7? The 10, we insert the 10 into the node. So looking at this one, we can see the key is 1, which just makes sense because we're in this particular thing. We're going to loop through until we hit the, well, actually, we want to insert it all the way to the end, aren't we? So we are at the tail, because the 10 has to go over here, right? So we're going to definitely go to the tail. Previous key, we should be the 9, yeah. Its next is going to be the new key. Its next is going to be the 10, which in turn has nothing, okay. And the new key's previous is going to be that 9. So the new key's previous is going to be that 9. So that's good. So the 10 links to the 9. The new key's next is going to be the current key. So the new key's next is going to be that 0. And the current key's previous is going to be the new key. So the current key's previous is going to be that 10. Cool. And then number of keys should increase by 1. How do I check that? Node. Number of keys should be 5, which makes sense. 1, 2, 3, 4, and then the 10 makes 5. Remember, we're not counting this as an actual key. So we've inserted that. I'm pretty confident that the insertion has happened correctly. While the current node number of keys is greater than the max key, which will happen now, the parent pair is here. The parent pair should refer to this guy. Parent pair with a key of 14 and a node that has a head of 14. So we're pretty confident that that's happened correctly. if there is a parent pair, and there is, then parent node and parent key should be set. So parent node. Ooh, this wasn't updated correctly. I've just realized. Number of keys is set to 1. Number of keys is set to 1. It should be 2, no? Because 14 and 26. Okay. More bookkeeping issues. And the parent key is the key 14. Okay. That's happened correctly. It's just the numbers aren't fully correct. B-tree node split. Keys left side is this one. It's 2, which makes sense because you're going to take 1, 2 on this side and then 9, 10 on the other side. Median is the node head. Previous is null. Int count equals 0 count. This one count plus plus. So previous, yeah. So this is a bit archaic now because I have a previous field I could use instead, but I'm just going to keep it because I back this. Okay, so the median should be the 7, good, and the previous should be the 2, also good. And just to clarify, the previous here should also say 2. Yes, okay. So left split head is node head. Yes. So left split, your head is the 1. Yes, that makes sense. Left split tail is a new tail. Left split num keys is equal to max keys. Oh, I did that twice. Okay, fine. I didn't realize. Okay, so previous next left split is, sorry, previous is next. So previous being the thing before the median. Previous is next should instead of pointing to the median should point to the left split tail. Okay. So previous is next should point to the tail, which it does. The previous is pointing to the 1. So the previous itself is key 2, this guy, which makes sense. Its previous should point to 1, and its next should point to the tail. I think that makes sense, yeah. Node head now points to median next. That head's previous is null. So now, basically, if I look at node, it should look like the right split. It should look like 9 and 10. So the head should look like 9, and the neck should look like 10, and it does. Okay. Left split tail, child, is equal to median child, which is going to be null, so I don't know if I can do much with that. And the median child itself will be the left split. Okay, I should check this. The median's child should be the guy with a head of 1, the left split, yeah. So it should be that guy. So 1, and then 2, and then tail, and then null. Yes, okay, that looks good. If there's no parent key, there is a parent key, so I think that should be fine. Okay, here we go. The median, which was the 7's next, should become the parent key. Oh, I see what's happened. Okay, hang on. If the parent key's previous, if the parent key's previous exists, that is, there is something before the parent key. That means, we're putting something. Sorry, head should equal median. Okay, I understand. I think what's happened. Basically, the 7 would have been placed here. In this particular instance, right? The 7 would have been placed there. The median's next is equal to parent key, which makes sense because the next should be the 14. The median's previous should be whatever the 14's previous was, which also makes sense. That's fine. And in this case, it will be null. If there's a previous, there is no previous. If there was a previous, let's say we're inserting something between 26 and 14. If there is a previous, if the 14 is there, then the parent key, then the previous says next should point to median, which is what we were doing. However, what I didn't do is say if that's not the case, if there's nothing if there's no previous, that means that the median we're inserting to is the new head of the node. I didn't write that in. which is why the 17 was being missed, because the head was still pointing to the 14, even if the 17 was being successfully linked to the 14. That's what was happening. Parent key previous is equal to median. Parent key previous is equal to median, that makes sense. And the parent node's num keys should increase. And we should return just the parent node. So either we return the new, yeah, okay. So I think now, there was some other issue, didn't I say? I said the number of keys wasn't being set correctly, which is a shame. Like, this was saying 1426. Like the parent node, is that the parent node? Number of keys is 1. It should be 2. That's another issue, because that will actually screw us up. Why did that happen? I would have thought that. When you push the 14 for the first time, you say tree node init, which sets number of keys to 1, which I thought would be why that's 1. Then you insert the 26. Oh man, let's see. I think the print will be correct, but I noticed that the number of keys is wrong. So we have 7 now, which is good. 7, 14, 26, 1, 2, 9, 10, 15, 21, 31, 33. But I'm nervous. If I was to say, let me get rid of the first print, and let me add the let me just like this. Num keys is equal to let's just see what it says. Current num. So no num keys. I think that'll tell me how many keys the code thinks we have. Num keys is 2, num keys is 2, num keys is 2, num keys is 2, num keys is 3. So it's really like not keeping track of things correctly. Sometimes it's too few, sometimes it's too many. Just keep going. So if I insert 22, it should insert it into this leaf, and it should be pushed to 3. It does, okay. So sometimes you're just inserting it into a leaf, it works no problem. What I just do, insert 23, which is small 26, which would go into here, num keys priest. So inserting into a. So I insert 24, which has a similar thing, except something like 24 we put here, which means 22 when pushed up to the top, which it did, but number of keys did get increased though. So the increasing is happening. So maybe it's the original number of keys. Like, you know, I said equals 1 line. Maybe this side that's not happening. I mean, I'd be surprised because I would have thought. Let me go way back. When we add 14 at the first sort of push. That's the first push. Let's see what happens. Oh, okay. And then when I add the 7, or add the 1 and 3, what happens? This is 1, this is 2, and this is 1, 2, 3. Okay, good. Then when I add the 21, what happens? 1, 2, 3, 4, 1, 2, 1. Fantastic. When I add 7, I think that's when the push happens. Oh no, sorry, 7 will be here, so maybe not. That's fine. 1, 2, 3, 1, 1, 2, 3, 4. Good. The 31 I think is what happens. We have 31 here, which is 26 push up. Here we go. Okay, so what happened? 14 and 26 didn't get implemented, and 31, 1, and 3 didn't get decremented. Or rather, it did get decreased, but not. Okay, so numbers are maths anymore. 15, 21, keys are 2, which makes sense. Okay, let's see what happens. So it's splitting. I'm assuming it's like that math. This math here is like really wrong. So we had 14, 2, 7, 9, 3, 1, 2, 3, 4. 4 keys. Everything's correct up until the point where we insert the 31. Okay. And just to clarify one more time, when we insert 31, 31 gets into here, which equals 5 keys to be produced, and the code does successfully push 26 up to the correct place. It just doesn't realize how many keys have been put. How interesting. The fact that it puts 26 in the right place tells me that it found the parent key correctly. It knows the parent key is 0, it knows the parent node is 1. So why this didn't happen, I'm not too sure. Anyway. So when we make the split, right? We figure out the median, which is the 26 here, that's fine. We figure out the median, and then left split, we malloc the tree node in order to make left split. Left split's head is the node head, so node head is 15. That's fair. Node head is 15. Where am I? Yeah. Leaf is true. Tail is the 0. So and the max keys over 2 will tell us how many keys there should be, which is why I think this time was correct. Because the max key, this is the left split, max keys over 2 goes to left split num keys. Previous. Next. So the thing right before the median, its next would be the tail. So this guy right before the median, no, sorry. This guy right before the median should point to tail. Okay, and left split tail should previously point to the previous. So this tail may should point back to the previous when we insert this previous key. Cool. Node head is equal to median next. Node head is equal to median next. So node head, node being this parent node. Yes, node head should point to median next. So the head should now go here. The 31 that got inserted because of the change. 31 that the node head's previous should be not this node number keys. Node number keys. Okay, is equal to node number keys. So node number keys is 4 minus the left split number of keys minus 1. But the idea is it should be 5 at this point, right? Like number of keys is 4, but then because I inserted the 1 and 3, because I inserted the 31, shouldn't be set to 5 now, unless it wasn't set to 5. Because if it's 5 minus the 2 minus 1 would give you 2. But it's 3. Left split number of keys. Left split number of keys. Node number of keys equals node. Maybe it's an issue before I just realized that I printed stuff out. Like maybe it's always an issue. Node number of keys equals node number of keys minus left split minus number of keys. Sorry. Node number of keys minus the left split number of keys minus 1 left split number of keys. The thing is, like, if the numbers are wrong, I'm splitting at the wrong times. I do the division at the wrong times. Is the issue. When we do the split, like you are the right split. So number of keys will be 5 because of the 31 getting added. B tree node insert. B tree node insert. Yeah, like the number of keys get increased by 1. After I call the B tree insert, can I like print the tree? Just get an idea of yeah, so this is 5. Okay. So if this is 5, just do it. That means that function works as expected. B tree node split. So when I get here, 5 and 2. So it is 2. What? So I'm implementing something. I'm implementing wrong. So it knows it's 2. What if I don't have this line? What happens then? Is the parent point at the node? Okay, so when I'm implementing this, implementing the bottom guy, I'm implementing the top guy. Which suggests to me that I'm not pushing the right thing onto this tag. It's not good. Although I am putting things in the right place, apparently. So that makes sense. I'm so confused. Why is it? So this is only this increment that causes. When I put this increment, it's this increment that causes this increase by 1. Because if I don't have this line, then this doesn't increase. So this increment is causing the child, the leaf to increase by 1, not the it's causing the child to increase by 1, not the parents to increase by 1, which was meant to happen because of the addition of the median. Actually, how does that? So when I call B tree node split, right? I give the current node, I give the parent key and the parent node, I give the tree, and I'm giving the velocity thing. So, I mean, all I'm doing is doing what's before I change the structure of the stack a little bit. This needs to be above. I need to add the current node before I reset this to be the okay. Well, that's annoying. Yeah, okay. So I was putting the wrong thing on the stack. Wow, that's a real shame that I've done that. I'll probably speed through that like times 10, like. Okay, now it's doing exactly what I think it should be doing. So this increases here. Okay, so if I put all of these guys back in, well, maybe I'll put. Okay, let me get rid of the verbosity thing. Get rid of this. That was a bad bug. I didn't think hard enough. I just yeah, didn't think much of it and then put it the wrong way around. I went too far. What? Does that not work? Okay, whatever. How do you do the thing? I always forget how to do this. Oh, there we go. Okay. Please work. That's, I think, correct, right? There's like 2 Gen 1s and then 3 Gen 2s. I think that's right. It looks pretty good. Okay, I'm gonna say that I think it's correct. All right, and after all of that, how long will we go for? Like a couple of hours or something? After all of that, I finally did the tiny little optimization I wanted to do. Now we can do the deletion. All right. So I have managed to do the insertion, right? With a little bit of optimization that maybe wasn't necessary. So yeah. So now we get to look at deletion. Some of this code is really gross. I'll see what I can do to fix it up later, but you know, it's not too bad, I guess, but it's a little bit gross. This is annoying, but I don't know if I can do much about it. The amount of nesting. This is not too bad, although this maybe looks like it could be a... it's kind of specific, I guess. This can go, as can you. You're gone. I'll get rid of most of the comments. Oh yeah, I guess all this, okay. Hopefully all this code makes sense, especially with the video in hand. So I'm going to get rid of most of these comments. You were more explanation than anything else. Yeah, okay. So a little bit of annoying nesting in places. Readability is not too bad. But yeah, get rid of you. Get rid of you. I think I can figure that out. Get rid of you. Yeah, so this still prints the 0 at the end, the key, but the tail piece as well, tail key as well. So okay, I think I made a new branch for this. Yeah, I'll just add got rid of some comments. All right. Okay, so we have that, which is cool. So yeah, deletion. Deletion's a little bit weird. I did sort of try it a little bit, but then I kind of realized that it required a bit more thinking than I first thought. So this isn't necessary. This was an example I was working through. Okay, so let's discuss a little bit. So deletion. The general idea, of course, being you have some kind of tree and you have some numbers in the tree, or keys in the tree, and you delete one of the keys. You want to delete like the 73, or you delete the 50, or the 72, or whatever, right? You want to delete a number. So you're given a key, K, and you want to find it in the tree, and you want to remove it from the tree. Now, what makes this a little bit annoying is the fact that, of course, after you do this deletion, you want to ensure that all your properties, right, these properties and the general, organizational sort of structure of the tree is maintained. You don't want to lose those properties. So I think one of the biggest properties to remember is all of the non-root nodes need to have at least this number of nodes in it. So that is, since the hyperparameter is n, right, a node can have at most n keys. The minimum for all the non-root nodes is decided to be this number. So, for example, if you have if n is equal to 5, that is, you can have a maximum of 5 keys. Overflow happens at n equals to 6, or not n, but at 6 nodes, which means the left split will get 2, the right split will get 3, and the median will get pushed up to the top. So the minimum should be 2. Right, this minimum is chosen so that after a split, the smaller number is that minimum. So in this case, 5 divided by 2 with ceiling gives you 3, minus 1 gives you that 2. And if it's an even case, if n equals 4, then overflow happens at 5, in which case, overflow happens at 5, so 2 will go to the left split, 2 will go to the right split, 1 will go above, the median will go above, right? And so this 2 again is the same as this value, 4 over 2 with a ceiling minus 1. All these nodes of B tree have M2 minus 1 keys. Oh, I know where that doesn't from. M2 minus 1. But the m they use refers to, so m is defined as the number of kids you have. So my n is different to the m, so this should be n plus 1. N is equal to m, the m that you here is equal to m plus e. The m that you here is equal to n plus 1. So I got this up. Okay, so let me see if I can do that again. So one of the more important properties to remember for B trees, for this deletion stuff, is this one. For all the non-root nodes, all the non-root nodes have to have at least n plus 1 over 2 minus 1 nodes in them, or keys in them. So remember, n refers to how many keys each node can hold, like a maximum capacity. And so the idea is this guy is defined as, for all the non-root nodes, you have to have at least this many nodes in them. And the reason for that is based on splitting from the insertion time. So if you think about, like, let's say n equals to something like 5, that means overflow happens at n equals 6. So when the splitting happens, 2 will go into the left split, 3 will go into the right split, and 1 will go above, right? So that 2 should match this formula, I think. So 5 plus 1 whole thing over 2 minus 1. So 6 minus 2, so 6 divided by 2 is 3 minus, yeah, right? So that 2 from the split matches that number. So the minimum, that's why the minimum should be this. Because the smallest you should get is during that split, and then you should never go beneath that, is the property that is enforced. And then for an even case, like n equals 4, that means overflow happens at n equals 5. I'm assuming it's just integer division, so the split would be 2, 2 with a 1 on the top, right? When the overflow happens, the median will go to the top. So we have 4 plus 1 over 2 minus 1. So 4 plus 1 is 5. I think it's ceiling. There should be a ceiling here. Because then it'd be 5 plus 1 over 2 gives you positive 3. Minus 1 gives you 4 plus 1 is 5 divided by 2 gives you positive 3 because of the ceiling. And minus 1. Yeah, so I think that's right. 2. Yeah, because the minimum should be 2. If it was floor, then it would be 4 plus 1 divided by 2 gives you 2 minus... Yeah, so that wouldn't make sense. So I think this is the formula. So... And just to double check, so with 5 plus 1 divided by 2 gives 3, which is already an integer, and then minus 1 gives 2. Yeah, so I'm pretty sure this is good. So, yeah, all the non-root nodes need to have at least this many nodes in them, which is important. Alright. So for the deletion, the basic idea is as follows. You're given the key, k, that you want to delete, and you want to find it in the tree and remove it. And what I should do, actually, is I should swap the way I've written this. It should say this first, then this afterwards. So given the key k, find it in the tree, and then if it's a leaf, if the key that you're trying to delete, if k is in a leaf node, then you can pretty much just remove it, right? And then the extra check you have to do is if removing k causes the number of keys in the node to be less than the minimum allowed, then you have to do one of the following. You have to look at the sibling node, right, and check if it has at least n plus 1 over 2 nodes. So let's do this slowly, right? If removing the key from this leaf causes the number of keys in the leaf to be less than the minimum, basically is what I'm saying, then we have to look at the sibling. Look at a sibling node and check, a sibling leaf specifically, and check if it has one more than the minimum node. If it does, then we do this case. So for example, right, let's say we have this kind of structure over here, this tree, n is equal to 5. Minimum is therefore 6, yeah, it's 2, right? The minimum's at 2. It's still correct, even though I got the formula wrong. So what do? So we're trying to delete 16, right? That's what this is saying. So we delete the 16. We notice that the number of nodes is too small. The number of keys in the node is too small. It's a leaf node. Number of keys are too small. Because we need 2. We only have 1 at this point. So we look at the sibling node. The sibling node is sort of on the same level, right? Shares a common parent, and we check how many nodes do you have. Well, this one, I don't know why I have red stuff in here. This one has 3, which is one more, at least one more than the minimum. Okay. So what do? So we're in the first case, right? What we do is in this case, the sibling node is to the right, right? This is the node we deleted from. The sibling node is to the right. So in this case, we take the smallest key from the sibling node and the separator key in the parent. Separator key meaning the key that is bigger than everything in us, but smaller than everything in the sibling node. Sort of, it acts as like the in-between key, right? Is the separator key. So we take U and we take U. And as the arrows suggest, the separator key gets added to us, right? The deletion node, and the sibling node key gets pushed up to the parent, right? So why do we do that? All right, think about why we do that. Essentially, we understand that we have to put something in here because it's too few keys, right? We have to put something in there. We know the sibling key has a key to give, right? Because we said this. The sibling key has at least one more than the minimum, right? So, the sibling key has something to give. If we were to just straight up give something over here, though, if the 21 was to just come straight over here, we'd have a problem because what would happen is the 21 is in this node, but the key that points to it is 20, right? Which is meant to be, so the key that points to it is meant to be bigger than everything in here, but the 21 is bigger than the 20, so we've contradicted our B-tree kind of structure. So that's why we can't do like a direct thing. Instead, the 21 goes up and the 20 goes down. The 21 is bigger than the 20 and so it's going to be bigger than everything in here. So it's okay if this guy becomes the parent key. And the 20 goes down. The 20 is also bigger than everything in here, so it's okay if it goes in here. But it's also smaller than the 21 for sure, right? Everything in here is going to be bigger than the 20, so it's okay if I use this guy as sort of the new separator and push this guy down. So this node basically receives from the parent, and the parent receives from the sibling, and the sibling basically just loses a node. That way, but it's okay if the sibling loses a node because we know for sure that we have one more than the minimum in the sibling, right? So that's the major idea. And if we can do it like that, then we know that we basically stabilized everything. This guy, even though it got something deleted, it also received something from the parent, so it will be okay. The parent, even though it lost something from here, it also gained something from the sibling, so it'll be okay in terms of not being too few keys. And the 21 got lost and didn't get replaced by anything, but we know it can be lost without any problems. So that's kind of how it works. So from here, you get this. The 21 moves up, the 20 moves down, 16 is gone, and the 21 is gone from here. All right, 21 moved up, 20 moved down, 16 is gone, 21 is gone from here. So that's what it translates to. And of course, I said, the sibling node could be to the right. It could also be to the left, in which case you take the biggest key from so this is the sibling, and this is the deletion node. This is the node that we're deleting from. You take the biggest node from the sibling. This is the separator key, right? Because it's the one that's sort of smaller than everything in here, but bigger than everything in here. So it's sort of the in-between guy. This guy goes down, and the 12 replaces the 15. So the sibling loses, the 15 gets replaced with the 12, and the 16, which got deleted, then the 15 comes in to take its place. So that's kind of the major idea. So that's if, first of all, we're in a leaf, and also if the sibling has sufficient nodes to do this. Now, if the sibling does not have sufficient nodes, if the sibling has exactly the minimum number, we know it won't have less, right, at any given point. So the sibling won't have less than this number. It should be +1. Won't have less than the minimum number, but it might have exactly the minimum number. So if that's the case, then it doesn't have any node that it can give, any key that it can give away freely, right? It can't just do that because then it will be in trouble as well. So in that case, we merge everything together. Before we were splitting nodes apart. Here, in this particular case, we're actually merging things together, and this was some working I was doing, which I don't think I need right now. Get rid of it. Okay, so in this case, right, k is 16. It's the same kind of thing where the minimum number of nodes is equal to 2. So I have all these squiggles. We try to delete the 16. This is my deletion node. We try and delete the 16, which means 18 has too few nodes, right? This node has too few keys in it. The sibling has exactly two keys in it, so we can't just freely give anything away. So what do? We take the deletion node, we take the sibling node, and we take this guy. We take the separator key, the one that is between, our deletion and our sibling. And we make them all into one node. Right? So take our node, the deletion node, the sibling node, and the separator, and put them into one thing. So the 18 from here, the 21, 22 from the sibling, and the 20 from over here. All of those guys became one node. And in this case, it was okay. The parent lost something, but in this case, it's okay. The minimum is 2, so that's fine. But if the parent ends up with too few keys, we basically have to redo this entire process, this entire idea of checking, we did a deletion. We basically did a deletion on the parent. So we have to repeat this whole deletion algorithm again, but on the parent node as the deletion node instead of the leaf node. Right? So it's like a recursive idea. Now, all of that was just for if the deletion is in a leaf. All of that was for if the deletion is in a leaf. So now we have to do what happens if the deletion is in a parent or in a non-leaf. Deleting in a non-leaf node of the tree, right? So keys in the middle of the tree, like non-leaf, can also be the root as well, so long as the root is not a leaf. Keys in the middle of the leaf act as separators, right? We understand this. Like when we have nodes that aren't leaves, and we look at their keys, those keys act as like bits of information. The child that they link to, we know for sure, like all of these children are going to be less than 28, for example. So the keys in the parent nodes, in the non-leaf nodes, are important because not just because, of course, they need to be there for existence reasons, but also because they sort of determine the overall structure of the tree. So deleting one causes us to lose what I've called organizational information, right? We lose a bit of, if I delete the 28, then like when I look at this link over here, I don't know, what this number is, what these numbers are bounded above by, I don't know anymore. So we lose that kind of information. So what do? Let's say, we're deleting the 28. What we do is we look at the left child, right? So, the link that's connected directly to the 28. We look at that child and take the biggest key, highlighted in yellow, or we take the smallest key in the right child. So we look at, technically it would be like the 33's kid, right? We look at that child and we get the smallest guy from there. Either one will be the replacement separator. Either one will be the replacement separator. Now, of course, so what do I mean by that? Let's say we take the 27. The 28 gets deleted. The 27 gets popped up to the top there. So this will just be 26 by itself, and the 28 will get replaced by the 27. Hopefully it makes sense that the 27 is a suitable separator because, everything in here, of course, is going to be smaller than 28, which means everything in here, of course, will be smaller than 27. So this is fair enough for sort of on this side, for this side. And then since everything is in here is smaller than the 27, then it's okay for the 27 to be the key up here, because that's what the definition of the key is, right? To point to a node that has everything smaller than you. So, separators are meant to be that so that, your left child, everything is smaller than you. On the right child, everything is bigger than you. So if I replace the 28 with the 27, that condition is still holding. So that's why that kind of works. And the same kind of logic can be applied to the 30. Everything here is going to be smaller than 30. Everything here is going to be bigger than 30. So if I use a 30 instead of a 28, should be fine. Yeah, and then but something to bear in mind, right? If I take this 27, push it up top, this node in here loses a key. So it's possible for the child node to have too few nodes in it, right? To have less than the minimum number of keys. Sorry, I keep saying nodes. It's possible for the child node to have too few keys. And so you have to apply the entire process again, I've went too far back, sorry. This entire deletion operation on the child, on the child node as the deletion node, and repeat the whole process. So very recursive ideas, right? So I kind of want to do this a little bit slowly. What's the time? 10:09. So I'll do this for like an hour. I want to try to design some stuff because I feel like this can be a little bit weird. Here's my understanding, right? We're going to have to locate the key, the given key. So we're going to have to, step one is going to be traverse the tree until we find the key, rhyming. And then just as like a caveat, or like as a little note, it's possible that the key does not exist in the B tree, in which case I believe we will traverse till we hit like a null pointer. And that should be our indication that, oh, we couldn't find it. I think that's true. So traverse, but assuming we find the key, right? We check. I think another thing I should say, actually, this is me thinking ahead a little bit, but I'll talk about it again later. Have a stack of, I think, key node pairs to keep track of the traversal. So similar to what we did before when I had that stack of key node pairs to keep track of like how far down we were going and like who the parents were. I think we'll need that again, and hopefully it'll make sense as to why. Anyway, so we find the key and we have this stack. If the key is if the node is a leaf, if the deletion node is a leaf, right? If the deletion node is a leaf, then then we have to do all this stuff. We have to find a suitable sibling, right? The leaf case was all about using a sibling, regardless of whether the sibling had enough keys or not. And then the idea, if the sibling has keys to spare, like has enough to give, I should also say find the suitable sibling and also find that separator key, because you're going to need that separator as well. Find the suitable sibling node. Find the suitable sibling node. I don't know why I underlined suitable like so aggressively. Find the suitable sibling node and find the corresponding parent separator key, right? If the sibling has keys to spare, replace or maybe move the sibling to the parent separator, and then move the separator to the deletion node. Now, depending on whether the sibling is to the left or to the right, it will like the exact positions of things might change a little bit, which is a little bit annoying, but anyway. Otherwise, merge the deletion node, the sibling node, and the separator in the parent. So in part A, I don't think you have to do any recursion because since the sibling has, keys to give, you're not going to violate the minimum number of keys condition. However, here, if the parent loses the or if the parent I lost my pen. If the parent has too few keys, use the parent as the deletion node and as the deletion node and use the stack to find its parent. Although, do I need to... If I'm deleting from a parent, that means it's definitely not a leaf. So maybe I won't need its parent. Maybe I'll need... I feel like, hang on, am I misunderstanding something? Because, like, let's say you delete from a child, right? And then the parent stuff gets pushed down, and that means the parent now loses, you know, it violates the minimum condition. Then I'll recall this entire operation on the parent now, but the parent is not a leaf, so we'll definitely go down to here. And then I use the children again. Right? Like I use the children in order to replace the parent. But maybe because I've merged everything together, that new child that has come from the merging will have enough keys to give back to the parent or something. Very strange. Maybe I don't need the stack. I don't know, because whenever I'm dealing with like the parent case, there's two cases, right? Either I'm deleting from a leaf or I'm deleting from a parent. Whenever I'm deleting from a parent, I only ever use the children, don't I? And then I might have to recurse into a child node in order to fix it up when I use it. Whereas when I'm in a leaf node, I only really use a sibling, which is on the same level, or the direct parent. So I feel like I don't really actually move that far up or down the tree. I could be wrong. Maybe I don't need the stack. Okay, fair enough. Yeah, so I don't need to use the stack to find its parent because it won't need a parent. It will need its children. Right? Okay. Anyway. Part 3. If the deletion node is a parent, like not a leaf, then what do I need? Look at left child and the right child. And maybe pick the one with more keys, just so that I don't have to do as much recursion. If using the left child, then take the smallest guy, take the smallest, no, the biggest, take the biggest key and move it to the parent. Which means when I delete, when I am doing, since I'm doing this recursively, I should keep track of like where I'm deleting from, shouldn't I? So maybe I should, okay. If the right child, then take the smallest key in the right child and move it to the parent. And then if the child has too few keys, it becomes the deletion node. Now, just because it's a child doesn't mean it's necessarily a leaf, right? It could be an intermediate kind of parent node. So we might redo this, but even this doesn't require to know any parents. So I really think that I don't need the stack. So get rid of this. Okay, so this is my overarching plan. I really think there's a lot of holes in this, and I'm worried that this isn't going to work the way I think it's going to work, but... Okay, I traverse the tree, I find the key. I figure out kind of the direct parent that the tree is from, and I figure out the direct parent the tree is from, and I figure out the key is from, sorry. I figure out the direct parent, and I figure out the direct, maybe even the direct key, like the parent key. That could be good. That'll probably make it easier to find the separator, if necessary. So I traverse. I find the key, I find its parent node, its parent key, let's say. Do I delete straight away? If I delete straight away, I can give like the next node instead, you know? I can say, because if the node is gone, I have to say where it was positioned. Because there's like replacement stuff that happens, isn't there? In the case where it's in a non-leaf node, when I delete a node, the child's element should come up and replace that deletion. So I need to know where I deleted from. Yeah, okay. Interesting. So I think I will just delete straight away and then keep track of where I deleted from. I think this makes sense in my head, but I had these constants left and right to keep track of like whether I'm picking the left sibling or the right sibling or the left child or the right child, like depending on context. So hopefully that works, but we'll see. All right. I think I can do this. I don't know, it's just a bit long-winded, but I think I can do this. All right. So we're gonna have the public function that takes in the tree and takes in a key. So what are we going to do? We're going to first traverse the tree, we're going to find the key, and I think we're going to go as far as to delete the key and store the parent node, the parent key, and the adjacent right adjacent key to the one we deleted. I think we're going to do that. That way we're keeping track of where we just deleted from by using the right adjacent key. So we're going to do that. All right. So I guess if the tree is null or something, or the tree root is null, is there anything else? Or the head is null for some reason. I don't know why that would happen, but then just return, because I think these things indicate that you didn't even build the tree properly, like you don't have anything in the tree, so I think there's definitely nothing to delete there. Otherwise, we're pretty confident that we can say btree node current node is equal to tree root. And I might go so far as to be like btree node parent node, the one that's the parent of the deletion node, is equal to, I'll say null, and the B-tree node parent key, sorry, I meant to say key, not node, is also equal to null, I think. I think I want those. Did I write that down, or did I just do that in my head? That's not good. I didn't write it down. Anyway, so while, I guess, current node, because I'm traversing through the nodes, right? I'm using the keys to traverse through them, but I'm traversing to the node. So while it's not null, yeah, well, it's not null. I probably need a current key as well, actually, don't I? B-tree key, current key is equal to current node head. Maybe I'll say tree root head, just to be a bit more explicit as to where we are. So while current node is not null, while if current key is tail, then current node is equal to current key child, and actually current node and then the current key is equal to the current node's head. Well, this might be null though, so I've got to be careful. Okay, so if the current key is tail, so if we're at the tail, then we've reached the end of like this node, so we should move down. Else, and actually the parent node should equal the current node. The parent key is equal to the current key, and then we should move down. Else, if it's not a tail, if the current key's key is strictly greater than the key we're looking for, then is it the same thing? Current node equal to the current key child, and then if current node, the key should point to should start the head, and we should set the parent. Yeah, I think it's the same thing. So instead of doing this, I can say if it's a tail or if it's like this, then do this. Else, if the current key is equal to this one, then I think I can break out, can't I? Because it's like I've managed to find the exact key and the exact node. The current node will be set correctly. Yeah, I can set it. I found it, so I think I can just be like this. Okay. And then what's else? Else is dumb, I think. I don't think I need an else. Hopefully. Now, if not current node, if we manage to hit a null current node, that tells us that we didn't find the key, I think, so we can return. I think. Maybe I should print it? Nah, it'll be fine. Done that. Otherwise, we have managed to find a current node, and therefore we managed to find a current key. Can I do assert? Is this a thing? Whatever. I thought this was a keyword. Maybe not. Okay, so we hypothetically found the current key. That is the key that we're trying to find. And I'm saying we should say we need to update the links of everything. So if current key previous then current key previous is next should equal to current keys next. We're skipping, so the idea is I have two kind of cases. Either the current key is here, and I have a previous and I have a next. The previous is next should point, do it in green, the previous is next should point past the key and towards the next, that's what this is. Current keys previous is next should point to the current keys next. And the next previous, so the current keys next previous should equal to the current keys previous. So that is this link. The next previous should point back across like this. That way, this guy gets kind of cut out. Middleman gets cut out. I said I wanted to keep track of the deletion location. So btree key deletion location is equal to current key next. I'm going to use the next as a thing, just in case if the previous is null. Next is definitely not null because I have that tail piece, that tail node. So I have that. If there is no previous, that means this guy over here, the key is the head. It was the original head that I'm deleting from. I just have a next and it points backwards to null. So that means the head of the current node should equal the current keys next, which means the current node's heads previous should equal null, right? Because the current head is now the next. That previous should point back to null. That's it, right? You point to null, the head is over here. There's no need to say previous next, because that's null. Okay. I guess technically, hang on. Is this... I think I could keep this line. I could take this line and make it the out. It's fine, it's fine. Okay, so I've managed to basically redirect the connection so that this middle guy is no longer present. And I've also kept track of where we're deleting from within the node. I think if I say free the current key, but I can't free it yet because I need to access the child, don't I? Well, maybe I can have that saved as well. btree node, the child node is equal to the current keys child. That way I have access to it before I free it. And then I free the current key. So I've redirected everything. I've kept track of the deletion location and its child node. And then I delete it. Redirect everything and delete it. And then I have a btree delete fixup, which takes in the deletion node, which is the current node, not the current key, but rather the deletion location, takes in some parent information, parent node, parent key, and the child node. And hopefully that's enough to do all this. And then we return, and it's happy days, hopefully. This should also be void. We do this. Okay, I need the actual names of things, so I need the types and everything. So I need a node, so B tree node, the deletion node is what I'm calling it. The deletion location I think is fine. That's a key, wasn't it? Deletion location is the key after where we deleted from. Parent node is given over here. The parent key is given like that, and the child node just like that. Okay, so a lot of parameters, and only half of them will be useful because it depends on the case. So if the deletion node is a leaf, then we handle it using the first case. So we're up to step 2 now. We have to find a suitable sibling node. How do I do that? So I need to make a sibling node. So B tree node sibling. I'll just declare it for now. I'll think about what I have to do. So what I would normally do is I would say the deletion location child. Does that work? The deletion location, remember, is the key after where I deleted from. And there's definitely going to be a key after because of that tail. So at the very worst, I'll be using the tail. So maybe there's always a child to the... I guess there's always a sibling to the... No, I'm dumb. Sorry. Sibling, not child. Sibling means I need to look at the parent. Ah, yes. Okay. So if the parent key is tail, that means I only have a sibling to my left. In the sense that it's kind of like, maybe this example is good. But specific, instead of deleting from the 16, instead of deleting from the 16, sorry. Imagine I'm deleting from like over here. That means the parent key is not the 20, right? The 20 would be pointing down here to this node. The parent key over here would be that tail, that extra tail key that I've added. So if this is my parent key, the tail, then I have no right sibling node. I have to look to my left, which means I have to go previous. If parent key is tail, then sibling is equal to parent key previous says child. I have to go back to the 20 and then go to the child. Else, in every other case, I think I can always say sibling is equal to the parent key next child. And I might also want a separator, don't I? So B tree key separator. So if this is the case, so let me think about this. I think the separator is the parent key's previous. But then here, I think the separator is just the parent key. Is that fair? Because like, if I'm using the right sibling, then I need to use my parent key, the 20, because the 20 is bigger than me, but also smaller than my right sibling. If I'm looking at my left sibling, then my parent key is going to be bigger than me, but also going to be bigger than my left sibling, so I can't use him. I have to go back one and use the one before it, who will be smaller than me, but bigger than my left sibling. Yeah, okay. So I think that makes sense. Separated key is my parent, or if it's a tail, if my parent key is a tail, then I have to go back one. Okay, I'm pretty sure that's correct. So I have managed to locate the sibling node and the separator key. Now, here we go. If the sibling num keys, oh wait, yeah, I think I had I had something like this, but I think I messed it up. I'll do this again. So min keys is equal to, well, not equal to, but so what was my thing again? See, it has a ceiling function. My minimum has a ceiling in it, so I feel like that's going to be annoying. I think this is right. If there's if I have 5 keys, it flows at 6, the minimum should be 2. 5 plus 1 gives 6, divided by 2 gives you 3, minus 1 gives you 2. If my minimum is 4, if my n is 4, that means the minimum should be 2, 2. So 4, 5, 2. Yeah, it is right. Okay. So if n is even, that means my minimum number of keys is, I think, n over 2, right? Because in the case of n equals 4, overflow happens at 5, which means 2, 2, 1. 2, 2, 1. Left split gets 2, right split gets 2, middle one goes up. So my minimum is this guy. If n mod 2 is equal to 1, if n is odd, like 5, then overflow happens at 6. My minimum is still 2. My minimum is still 2. Because 2, 3 with a 1 on the top. Is the formula just this? Have I overcomplicated this massively? Hold on, what? Maybe it is just that, yeah. Huh. Okay. Oh, there's also the case. Okay, hang on. Wait. Is it just that? 5 divided by 2, floor it down, gives you 2, which is 2, 2, 1, which makes sense. And then. So n equals 4. If n is even, n equals 4, then the overflow happens at 5, you get 2, 2, 1. Minimum should be 2, so 4 over 2 works. N equals 5, overflow happens at 6, so 2, 3, 1. The minimum is still 2. Yeah, okay. Well, then, lol. Min keys is equal to max keys over 2. Whoops. Okay, fair enough. I do have to be a little bit careful, I just realized, because it's possible if the I think I should give the tree. Because it's possible for the thing to be root, like the deletion node to be root, and if it's root, then I think something's gonna happen. So if the deletion node is lead, if the deletion node is equal to the root node, then that's it. I do need to subtract stuff, don't I? I have to say current node num keys minus minus, and I should only really do this if the current node num keys is less than the min keys number. Then do this. No point in doing it if I didn't actually, you know. Anyway, if the deletion node is equal to tree root, then the only extra thing is like, what happens if there's no nodes now because you deleted the very last one because into the root? If the deletion node or tree root num keys is equal to 0, I think I can just free the tree root. What have I done? Free the root and make the root equal null. Right? Because like, otherwise, you know, I mean, there's a lot of nesting, but deletion node is leaf. If the deletion node is equal to the like, I definitely have to return at this point if it's a leaf and the tree node root, because I don't care about fixing up if in the case where it's a root node with too few keys. Like, the root node is not counted when you care about the minimum number of keys condition. So if I'm here, then I definitely should return, but I think I should also do this extra freeing step. It's a bit ugly, but I'll leave it for now. I think that's okay. Otherwise, when we're not in the root, we're not deleting from the root, but we're definitely deleting from a list, from a leaf. So we find the sibling, we find the separator. If the parent key is tail, then we get the left sibling. Otherwise, we get the right sibling. Now, if the sibling's number of keys is at least the min keys plus 1, if it has at least the minimum number of keys to give, that's move the sibling to the parent separator and move the separator to the deletion node. Okay, so this is where things get a little bit weird, because I think depending on the direction of the sibling, things are going to change, which is annoying. So let's say we're using the right sibling, right? We're deleting the 16 and we're using the right sibling. So the right sibling moves up to the separator, and the separator moves down to the end, the right end. Right sibling, so the right end of the deletion node. And then if you're using the left sibling, if you're deleting the 22, then the biggest guy moves up, replaces the separator, which is fair enough, and the this guy moves down to the front to become the head of the deletion node, the head of the deletion node. So yeah, it moves to a particular end, which is a bit annoying. Maybe I can have helpers for that. I don't think I'm. Void move key to head of a node. So given and given. So all we're going to do is say key next is equal to node head, key previous is equal to null, node head previous is equal to the key, so that gets that link going. Key previous is equal to null, and the node head is equal to the key. So that's one helper, and the other one is void move key to the end of a node. So B tree node, and B tree key star key. And the idea is node tail I've got to be careful. I'll just say, I'll do a bit extra work. B-tree key before the tail is equal to the node's tail previous, right? And the idea is, but what if this is null? That'll be really annoying. If before tail's a thing, then before tail next is equal to the key. The key's previous is equal to the before tail. The key's next is equal to the tail. And the node tail's previous is equal to the key. So that's if the before tail exists. Else, if there's nothing before the previous, before the tail, that means this is like a brand new, there was like no nodes in here, which doesn't really make sense, I think. Does it make sense for the previous of tail to be null? Because there should be at least one thing in here. Otherwise something really bad's about to happen. But whatever. Else, this can happen and this can happen. I think the key's previous should be null then. And then also I think the node's head has become the key. If that's happened. Okay. It's a bit more involved. I don't actually think I need it. I could be wrong, but just for the safety. Okay, so I have an ability to do that. If there's a minimum, if there's sufficient keys, right, in the sibling. If the parent key is tail, right, that means we're using the left sibling. In which case we have to. Maybe I'll do this later. Hang on. Let me do the other stuff first. So first things first. How do I undo this? I need to get rid of the biggest key in the sibling. Maybe I can point to that straight away, actually. Hang on. The B-tree key, sibling key. So the sibling, if we're using the left sibling, then the sibling key, the sibling key is equal to the sibling's tail previous, which I'm pretty sure is not null. I'm like pretty confident. Sibling key is equal to the sibling head. If it's the right sibling, you get the sibling head, right? Otherwise, you get the tail previous. Tail, remember, is not a real key. It's just the greater than link. So I need to go previous in order to get the actual key. Okay, so I have access to the actual sibling key, which is cool. Maybe I can even do the deletion here as well, actually. Like, deletion in the sense of, like, rewiring everything. Maybe I can say void remove key given the node and given the key. So B-tree key prev is equal to key prev. If prev exists, then prev next is equal to the key next, and the key next is prev is equal to prev. We're kind of cutting out the key. If there's no previous, that means the key was the head, which means the key's next previous should be null, and the node's head should equal the key's next, as opposed to the key, because the key was the head. That's the only reason I need to pass this in, otherwise I wouldn't need the node. Okay, hopefully that works. Yeah, so here I was thinking, so left sibling, I'm deleting, remove the key, given the sibling, and given the sibling key. This does not do any actual freeing, right? I'm not deleting a key, I'm just removing it. I'm just getting it out of the thing. Else, am I going to do the same thing twice? Can I do this at the end? So we're basically, we do the first step. We're cutting out, wait. Oh no, wait, I shouldn't actually do this until I double check I'm in here. So first things first, we remove the key. So we cut out, you know, if we're using the left sibling, we cut out this key and put it, and that's it. We cut it out. Then what do we do? Then we have to take the separator key and add it to the front of the sibling node. That is, sorry, of the deletion node if we're using the left sibling. Or the end of the deletion node if we're using the right sibling. Ugh, so annoying. So we've taken the 18 out of here. We have to plop it in here. What's a good way to do that? I don't want to just replace the key value over here, because I need to actually move the physical object from here to here. So yeah, if parent key is tail, we're using the left sibling, which means, what did I say? If we're using the left sibling, we have to move key to head, given the node, it's the deletion node, and we have to move the key, which is the separator key. So we have to move the separator key from up top to the head of the deletion node. That is if we're using the left sibling node. Now if we're using the right sibling node, then we should move the key to the end. We should move to the deletion node the separator key, but we should be using the move to the end function, because we've got to move the separator key to the end of the deletion node if we're using the right sibling node. Okay, so I've done 2 out of 3 steps. I've removed from the sibling, I have moved the separator to the thing. I just now need to do the in-between step of actually, what if I insert the 18 so that it's like before the 20, or for the 21 I insert it so it's after the 20. Okay, I have an idea, but it's kind of dumb. I'll make one more helper. Void move key like insert key before this key. So given a particular Wait, don't I have to increase the count of something? Shouldn't I say node num keys plus plus or something? God, so much bookkeeping. Move key to the end, same kind of deal, right? Node number keys plus plus. Wow. Insert key before a particular key. So given a particular node and given a particular key. So if so, we're going to insert key to insert B-tree key insert behind this key kind of thing. So we're going to get a previous again. So the insert behind previous, we're going to get the previous. And then this is going quite similar, I think. If there's a previous, then previous's next is going to be the key to insert. The key to insert previous is going to be equal to the previous. The key to insert next is going to equal the insert behind key. And the insert behind previous is going to equal to the key to insert. Else, if there is no previous, that means what we're about to insert is the new head. So key to insert next is equal to insert behind. Insert behind previous is equal to key to insert. And key to insert previous is equal to null. That should be it. And then node num keys increments by 1. Okay. So here's my grand plan. I have the ability to insert a node behind another node. So after I've managed to get rid of... I've lost everything. So I've done all that, and then I do this decision making. Okay, so I've removed the key. I've removed the sibling key. I will now move the sibling key. Left sibling. Left sibling. So I have to insert the sibling key before the separator key. So insert key before key. I have to, in what node is it? It's the parent node, right? Parent node. It's the sibling key, and it's the separator node. And then I will move the separator to the head of the actual deletion node. Otherwise, if I'm using the right sibling, wait, did I do this the wrong way around? No. If I'm using the right sibling, I have to move the 21, I have to move the sibling key and insert it before the separator next. Because I'm inserting it behind the separator, not behind the separator, but behind the separator next. It has to go in front of the separator. So that's the idea there. So the parent node is the same parent node. Sibling key, if we're using the right sibling, it has to be inserted here in the 21. And then when the 20 moves down, the 21 will become the new separator. Ah, but I have to make sure I say that. The sibling key child should be the deletion node, shouldn't it? And that's true in both cases. So I can do this here. I think this is fair game, because the idea is that 21 is going to become the new guy that points to this guy. You know? So I think I have to say that. And what should your child be? Your child should be null, shouldn't you? The separator's child, because it's being moved into a leaf node, the separator's child should be null. So what did I just do? I moved a sibling up, I moved the separator down. So the children have to be kind of swapped around and stuff. Well, not swapped around, but have to be updated carefully. Okay. I believe I've handled, I think I've handled this one. Otherwise, merge everything together. So if not this one, else, else, okay. So what do I have? I have like a deletion node. I have a separator up top, and I have a sibling node, which could be, so either the deletion node is here and the sibling is here, or the sibling is here and the deletion is here. So I have to be careful. I think I'll make a separate function for this. Void concatenate node to key to node. It's very specific. So I need a B tree node, a B tree key, and a B tree node again. This might seem very silly, but for my purposes, for my very exact purposes, this is going to be fine. So this is what I have. I've got to be a little bit careful because each of the nodes will have a tail, but I should only have one tail by the end of this. I should probably return like the head of the node or something, right? All right, here's what we're going to do. We're going to say node 1 tail previous should not be null. So like B tree key, oops, end node 1 end is equal to this guy. I'm pretty sure this is not null. If it is, then I'm a bit screwed, I think. Node 1 end is that one. So the idea is, at this point, I think I can free node 1 tail. I don't really want it anymore. I want to get rid of this guy. Now, the node 1 ends next should equal the key that we're passing in, the separator key, right? And the keys previous should equal, to the node 1 end. That way we basically link you up to you and link you down to you. And then also your keys next should equal to the node 2 head, and the keys, and the node 2's heads previous should equal to the key. That way we link you down to you and you back up to you. All right, so we have that kind of idea. So I think I've done the linking. I've freed the tail. I actually think I can free the node 2, which is just the node structure. The node structure in turn, has a head and a tail and everything in between, but the actual structure I don't need anymore because this is no longer two separate nodes. These links, these connections still exist, but by freeing, I'm just getting rid of the surrounding structure. So I think that's legal, and I think I should do that to avoid memory leaks, because otherwise I think I will lose that memory, that structure. Okay, so I have this one. So I have this one. I think I've managed to do the connection correctly. So what I'll do is I will return node 1, I think. Now I gotta be careful. Node, the key has a child, doesn't it? But it should be set to null because the separator is going into a child, but this function could not possibly know that. Let me think. I also need to update node 1 num keys. So I shouldn't, hang on. Num keys is gonna increase by 1 plus the number of keys in node 2. So I shouldn't free it until I've got that calculation, and then I can free this, and then I can return, I think, is my understanding. So now, else, we're gonna concatenate all of this. Node 1, so like I said, it depends on if the parent key is a tail. That is, if we're using the left sibling, in which case the left sibling is over here and the right sibling is over here, the deletion node is over here, then we should concatenate node to key to node. We should give the sibling node, then we should give the separator, then we should give the deletion node. Else, it's like pretty much the exact same thing, except I swap u, whoops, with u. Which is why I thought I should write a separate function. Because that's the same thing twice, I just, the order in which things happen is flipped. Okay, so I've managed to hopefully connect things correctly, but I have to be careful because the separator child should be null. I end up not using a sibling key, naturally, because that's only really important. Should I only really make the sibling key like here? Because I only really use it here, right? But I need to remove it straight away, so maybe it's fine, actually. Like, I need to use it over here, so I'd have to do if parent is tail or otherwise, again, which is annoying, so I think that's fine. Else, do all this. So all of that, in theory, should be enough for 2A and B, except if the parent has, of course, if after all that, wait, I need to make sure the parent number of keys is updated. When I did all this, what did I actually do? Okay, so I think I have to say the parent node num keys minus minus. I think I have to decrement here because I haven't done it before. I updated, I didn't use the return value. Hang on, wait. How did the edges change? Let me think about that. Because, like, I'm bringing the separator down as well. So if I delete from the right, if I use the right sibling, okay, it's this one. If I delete from the right sibling, 20 goes down. So it's the tail. It's the I think it's the next, so the key after the separator is the one that should take this node as the the child. Hang on. So just declare node. The merge node is just something I've made, and then we very quickly give it a value, so I don't have to worry about that too much. We update separator's child, we update the parent node, and I think I should say something like, I think I should keep track of like B tree key after the separator is equal to separator next before I do all this. And I think it's the separator after separator's child is meant to be the merge node, I think. What about in the case we're using the left sibling? Does that change anything? If the sibling is on the left side, then the separator is this guy. The separator is still that guy. So I think if I say next again, yeah, I think that's fine. I think it's always the guy right after the separator who should be the one to take this merged node as a child. Because that next guy will be... Ooh, actually, is that true? Hang on, I need to draw a few examples. Hang on, I'm not so confident now. Let's say we have 9, 15, 20. This guy has a child that's like 12, 13. This guy has a child that's like 17, 18. Right, and the idea is the minimum should be 2 because the maximum, let's say n is equal to 4, minimum should be 2. Yes, okay. So in the case where we delete a 12, then the 13, 17, 18, and the 15 should get merged together. Yes. 13, 15, 17, 18. In which case, yeah, this guy should be the one to link all of this together, which is the guy right after the separator. Because the guy right after the separator is definitely going to be bigger than the right sibling, and also is going to be bigger than everything there. So that's fair enough. Okay, so for the right sibling, for sure, the guy right after the separator is the right person. So that's fine. Whoops. What about if you're using the left sibling? So what if you're deleting from this side? Then the left sibling. So the sibling, sorry, is over here. So you'd still make 12, 13, 17. The separator would be this guy. I think we did that, right? We said the separator is the parent keys previous if using the left sibling. Yeah, good. Okay. So the separator is this guy. And then 18, wouldn't it? Because that guy's gone. So that's the merge node. So the appropriate parent for this merge node would again be, so the 15's been moved down, so it would be this guy again, which is the separator. Okay, I'm pretty confident that's right, yeah. Okay, that's fine. So the after separator, the child should be this merge node. The separator's child should be null because we've put the separator into a leaf node, I should say, and the parent node has lost a separator, so that's happened there. And the idea is, if the parent node num keys is less than the minimum number, then we can call, hopefully the idea is we can call this btree delete fix up again. We've already removed something. The deletion node becomes the deletion node is this parent node. The deletion location is the after separator, isn't it? That's lucky. Is the after separator. The parent node, I don't know, but I don't think I need it because I don't think I'll be using this section. So I'm going to call this null. The child node what? What was child node meant to be? The key's child. Oh my god. Okay, hang on. So I moved the 15 down. Let's say there was no 9, right? When I moved the 15 down, because, I deleted the 17 or whatever, or I deleted the 12, I moved the 15 down because that was the separator. And let's say this isn't the root node, so there's other stuff as well. Like 40. 41, so I delete this 12, so then the transformation of this is I have 20 over here, and then I have 12, 13, 15, 18 over here or something. Like that. And of course there's the tail pointing somewhere else. So when I try to fix this now, because this guy has too few keys now, what do? I have to... Hang on, let me look at my notes again. I have to look behind at numbers smaller than the 15. But in this case, there are no numbers small. Well, there is, but... So what would happen in this case? The 18 will get pushed up, become the parent of this guy? But what happens to the 20 then? Oh man. When you delete from... When you delete that 15, you're left with just a 20, which is of course linked to some 40, 41 thing as well. So that is because I don't want this one to be the root. This has to be fixed up. Since it's not a leaf, I have to rely on... Maybe I'm not meant to make... Maybe I'm meant to call the function before I actually finish things off. Like, when I do all this merging together, maybe the 18 is going to get pushed up before I establish everything, you know? This is kind of weird. Insert the key right before the key. So insert the sibling key right before the separator next, and then move the separator to the end of the deletion node is what I'm saying. Because I wanna move the sibling key in, and then I wanna move this is for the right sibling. Yes, the right sibling, because I want to move this big guy to the end of the deletion node. Yeah, that makes sense. Okay. Otherwise, I figure out the merge node, I figure out what happens after the separator, and I do this whole concatenation thing. Like maybe this line shouldn't be here, is my thinking. I think I have to do something like this. Hang on. The child node is going to be the merge node, and the tree will be the tree. Else, if there's no issue, then I think we can do this. I think it's something like this. Like, the after separator is a good candidate to be the parent, but if there is an issue where the parent node doesn't have enough keys, I think we can happily sort of we can use the fix up function again to like clean that up. We know that it's a leaf. We know where the deletion happened. We know sort of where the what the node is, where the node happened, we know what node the deletion happened in, and we know where where the deletion was in terms of the keys. Parent node and parent key, we're not gonna have to use them anyway because it's not a leaf. Child node. Why did I want to give child node again? I really forgot. Like, what does this child node represent? Deleted keys child. Which I guess would be the merge node, right? But what was I going to use it for? I don't think I need that. I really don't think I need that. I might get rid of it. Anyway. Because the fact is I can access children really easily. But I guess I can't access it if I freed it and deleted it. Maybe that's the issue. I guess that's the issue. Yeah, okay. Maybe I do need it. Anyway. If it's a leaf. Else, if it's not a leaf, then we have to handle this stuff. If the deletion node is a parent, look at the left child and the right child and pick the one that has keys. So, left child, I think what I can say is B tree key, or node rather, left child is equal to the given child, I think, is the whole point. I give the child node. This child node, this left child, contains the keys that are smaller than the guy that we deleted. I hope. in theory. And then B tree node the right child is equal to the deletion location, which is a key, its child is the idea. Because the idea is the deletion location is meant to point to the key right after the deletion. So going to you and taking your children is going to give us the children that are bigger than the key that got deleted, is the idea. I'm kind of put off because when you do this merging thing, the 15 got deleted, quote unquote, but the biggest thing here is 18, which is bigger than 15. I feel like but I guess this 18 is still smaller than everything in the parent up top. Like everything, not everything, but it's still smaller than what comes after the 15 here, kind of thing. So I think it still kind of works out. Anyway, if left child num keys is greater than or equal to the right child num keys, then we're going to take the left child's end. What functions have I made? I feel like these might be helpful. Then the like new parent or whatever is going to be equal to the left child tail previous. We're going to remove this key from the node, the left child node. We're going to remove this new parent, and that should hopefully handle all of the like counting logic and stuff. Maybe not. This is why I'm so bad at bookkeeping. Okay. So if the left child, we remove that guy and we put him to the top, insert key before key. So in the parent node, that is the deletion node. In this node that we're inserting in, the key to insert is going to be the new parent, and the insert behind is going to be the deletion location, I think. Right? That makes sense. Like, up top, you're trying to insert the new parent into the deletion node. And hopefully this guy, yeah, okay, at least you do some bookkeeping. Okay. Else, if we're using the right child because it has more keys, then maybe something along the lines of if left child num keys is less than the min number of keys, then B tree delete fix up, given the deletion node, which is the left child, given the deletion location, which would be what? Which would be the left child tail, because we deleted right before the tail. The parent node would be me, the deletion node. The parent key, oh god. What is the parent key? Didn't I delete that guy? No. The new parent, right? the whole idea is the new parent's child is meant to equal the left child, right? So if I delete it from... I think this is right. God damn. The child node is the left child, I think. Oh, no. Uh... the new parent's old child. Yeah, whatever its child was before, then remove it, and then insert it, and then reset the child. And then the old child and the tree. And the whole reason for that is so that I can get the left child that was a... yeah. Yeah, and that's it. Else, if there's more kids in the right... if there's more keys in the right kid, then the new parent... this is kind of a template, I guess. Copying and pasting is bad, but let me just take a look. The new parent is, I think, equal to the right child head, isn't it? We're going to be taking the right child's head, we're going to take the right child's head and use it as the new parent. The new parent's old child is the new... that's the same thing. We're going to remove the key. We're going to remove from the right child. We're going to remove the new parent because, yeah, and just to clarify, that handles the logic behind, like, if it's a head, right? The node head should be the key next. Yeah, so that should be fine. New parent's child is equal to the right child. Oh, is that right? I don't think so. Because the child is always... you're always pointing to guys who are smaller than you. The idea is, if you're the head, you're the smallest guy in the right child, so you should definitely be pointing to the left child. In fact, yeah, your whole job is to replace the separate, or the whole job is to replace the guy that was deleted, who would have been pointing to this left child, the child node. So yeah, you should definitely be pointing to the left child. And then since I removed a key from the right child, I have to check if the right child number of keys is this, then the fix-up is the right child. I deleted from the right child. The location would be the right child head. The head was deleted, which means this head pointer is now pointing to the new head, the next guy over. When I called remove key, the head would have been updated. The parent node would have been deletion. The new parent is the parent key. Is that right? Hang on. What is new parent again? The right child head. I deleted from... hang on, what is this? The parent node is deletion node. I backed that because we did... that's the deletion node. We deleted from a child. The deletion node is the parent. Ooh, is it? Yes, it is. Sorry, it is. Of course it is. The parent key, though, I don't think this is right. I don't know why I said this. The parent key was the parent of the right child or the left child. So the left child is the child node, which means the parent of the left child is the parent of the child node. And the parent of the child node Wait, no, I think I'm getting confused. The parent key refers to the parent of me. Parent of what got deleted. Correct? When I used it for the first time, parent key is referring, yeah, to the parent of me. So when I do all this, parent key, like the left child got deleted, which means the parent node is the deletion node. That's the guy above. Who was the parent key that pointed to the deletion node? I'm very confused right now. Hang on, when do I use this? When do I use parent key? Oh yeah, I use it a lot. If the left child num keys is less than the min keys, then I have to I have to call delete fixer using using the left child, because that's the node where the deletion happened. I have to indicate where the deletion happened. It happened at the tail. I think the issue is because the child node refers to the child of the key that was deleted, it's actually quite hard to give the the parent key, right? Because that parent key is gone. I removed it, which is what caused this child to have to be raised up to become the new parent. It's almost like I have to give. So maybe it is new parent. Maybe the new parent is the guy, because the position of, like, at least the position of the new parent, because that is usually the information I care about. It's where the new parent is. Are you the tail? Are you not the tail? I kind of use that key to figure out if I should use the left sibling or right sibling kind of thing. So if the new parent really is the replacement, then yeah, maybe we're fine. However, over here, I think I should say new parent next, because the key that points to the right child is not the new parent. The new parent points to the left child. So I think, yeah, I think I'm good. I think I'm fine. Okay. And then I guess that's it. Okay, in theory, I've followed the template and I've completed it, but I don't think I'm correct at all. So this is going to be fun to debug. And I will debug tomorrow, probably. Let me see if it compiles. That's like the number one test, right? How far back? Here we go. Oh, God. Let's see what happens. Let's start small. Let's say we have a 9, and then we B-tree delete, and we delete the 9. You know, nice and simple. I can't believe it compiled. That gives me more fear, honestly, than if it had just blown up in my face. A.out, that's it, right? Okay, well, you know what? It didn't print anything, which is a good start. It means that, you know, something got deleted. Fantastic. Let's say I do this, and then I shouldn't, and I delete the 15. And I'm stuck in an infinite loop. Well, that was short-lived. That's interesting though, because it's all in the root node. So okay, so if I delete the 9, it's okay, but if I delete the 15, there's a problem. How intriguing. That's so interesting, because if I use dash G, right? I'm just curious. I shouldn't do this now. It's almost midnight, but I'm just trying to figure out, because this is not true. Parent node is equal to null. So while current node, if it's a tail or whatever, that's not going to be true. Else if it's this one, then break. Oh crap, I didn't, that's what the else is for. I said I don't need an else, didn't I? Else, I have to move the current key along. No wonder it's stuck in a loop. Wow. There you go. Okay, cool. And then if I have a 26, and I want to remove the 26, cool. What if I want to remove like the 15? If I want to remove the very, very start, the 9. Fair dues, okay. Okay. I'm like getting a bit braver. Okay, 1, 2, 3, 4. What was the last thing I just did? 1, 2, 3. Okay, wait, hang on. Let me not be this brave yet, because 1, 2, 3, 4. Let's say 5. So this happens. A resize happens. So now we've got some layers. So I think the thing at the top will be 14, because that's the median, right? 1, 2, 3. So let's say we want to remove a child thing first. Let's say we want to remove the 9. That should be sort of one of the leaf nodes, so hopefully it's not too bad. Although I think that will, yeah, there you go. That does cause, like deleting a 9 will cause like a fix up requirement, because, well, let me get rid of this first. Let me double check what the thing looks like. So if I delete the 9, that will cause this node, I got it wrong, sorry. If I delete this 9, that'll cause this node to be too small, right? Min size is 2, but the number of nodes in here will be 1, so that'll cause the fix up thing to have to happen. And that's the reason why it was working so far, is because I don't think the fix up really had to happen yet, because it was the root node over and over again. Now that it's actually needing to do some stuff, like do something interesting, it's segfaulting. So let me do that one more time. So let me just confirm that it's broken, and then let me just run and debug. Let me just see if it, because it will crash on the line, which is good. Oh, interesting. So new parent must be null, which shouldn't have happened, because tail is meant to be pointing to something. So that possibly indicates that I've done something really bad, which is a shame. Like left child, the tail should be something legitimate, and it should point to something, assuming, oh dear. Let me print the tree real quick before the deletion, just so I remember what it looks like. Yeah, one more time. So crash is there. So the left child, for example, I'm assuming what's happened, let me just think about this. Why are we in here, actually? If the deletion node is a leaf, I would have thought the deletion node... unless, sorry, yeah, so what's happened is I think the 9's been deleted. Yeah, I don't think it should be in here. Okay, I think what's happened is the 9's been deleted. We figured out a sibling. We merged everything together, 2 plus this plus the separator. And then it's all become one. It's all meant to become one node. Actually, it's actually a bit of a weird case. What's meant to happen is the 9 gets deleted. The sibling doesn't have enough nodes to just give one, so everything has to be merged. But you have exactly the number of nodes to do that merge, and so the root basically goes away. I don't know if I've actually handled that case correctly then. I like stumbled across a bit of an edge case. If parent key is tail, so blah blah blah. If it's a leaf, which it should be a leaf, I'm pretty confident it's a leaf. We do all this. If the parent key is tail, is the parent key tail? I guess it. No, it wouldn't be, because 9 is like smaller than the. Yeah, it's fine. So it's not tail. So we do right sibling stuff all the way through. Sibling should be the parent key next child, so it should be you. Sibling should be the sibling head, because you will be the guy that gets brought in if necessary. If there's enough keys in the sibling, there isn't. So else, the merge node after separator next. So separator is you. Yes. Separator next will be this guy, the greater than the tail thing. If parent is tail, that it's not. So otherwise merge the node. You take the deletion node, you take the separator, and you take the sibling. And then you make a big node out of it. And then what? Yeah, see, I don't think I handled this very well. The separated child is null. Yep, and the parent node number of keys decreases by 1. How intriguing. I mean, I can try like brute force my way through it. If the parent node is equal to the tree root and parent node num keys is equal to 0, then I think what I do is I say free the parent, free the root, and basically this merge node I've created becomes a new root. I think. Because if there was only one thing in this parent root, that means there's only 2 sibling, like there's only 2 kids in the next generation, in generation 1. That's always true, regardless of how complex the structure is. If there's only one thing in the absolute root, if there's only one key, then there's only 2 kids in generation 1. And if those have all been merged together, that should just be the new root, right? So free the current tree root, then tree root should become the merge node, and I think we can just return, to be honest. I don't think there's much more to check, because yeah, you've deleted from the tree root. Like normally I would want to check this, but I think I don't want to check that here. In this case, I actually just want to move on with my day. So maybe this will be okay. What did I delete again? Yeah, there you go. Yeah, hang on, sorry, because I printed it twice, it looks weird. But after you delete the 9, you just have those guys merged together to make a thing. Wow, okay. Let's say we have 103 and 21, and I want to delete from the tree, I want to delete 26. What have I done? Oh. Does that make sense? Maybe I should use the visualization tool. Hang on. So a few steps to follow. 9, 15, 26, 2. So 9, 15, 26, 2. 9, 15, 26, 2. 14. 14, 103. So 21, yeah, 21. And then this 26, I'm going to try and delete. So 915 on the top. Oh, it's wrong. Okay. Fair enough. All right, we'll have a look. Let me print before the delete. I'm pretty sure these things are deterministic, right? There's no way. So if I go back. Oh, wait, is it wrong before I even... Oh, sorry, it's because this is wrong. Oh, I've done the whole thing. Oh, I've done awful. Degree refers to the number of kids, so you're supposed to do... Oh, okay, well, I've just wasted everyone's time there. Okay, hang on. 9, 15, 26. I did think that the kids started splitting a bit early. Anyway, 2, 14, 103, 21. And then, so 14, and then 2, 9, 15, 21, 26. Ooh. Wait. Oh, I'm looking at the wrong thing. 15, 21, 26, 103. And then after delete, then yeah, that wasn't very exciting. Okay, let's say I want to delete the 14 now. It's a bit more intriguing. Once again. Yeah, so this case of like if I'm deleting from the root and then the root completely clears out because of it, I don't think I've handled it very well. It's almost midnight. Can I get it done in 3 minutes? It's something about like... if... What do I want? Yeah, the root node is the only one that can go to 0. So how do I handle that in this case? If I'm deleting directly from the root, it's not gonna go through this leaf thing. So this logic here, this logic that I added won't apply. Instead, I do all this thing. You know, in the leaf logic, I check if it's a root and I do all that. But in the non-leaf logic, B-tree node. Just to clarify, what happened? I got 21 and 103 only. I didn't even get the 15. How intriguing. So before I deleted the 14, I had, 3 generations basically. Interestingly, this says num keys is equal to 1, even though it technically should say 0 if anything. That makes me think that I might have not updated something correctly, like regardless of all this root stuff. Because I think what would have happened is the 14 would have been deleted, What should I do in this situation? Like, what's meant to happen? When I call this, when I call delete 14, the 15 is meant to kind of replace it. So here, which I guess makes sense with the algorithm, like you pick one of the kids, you take the head and you push it to the top. So I guess that is what's meant to happen. So why didn't it happen then? Left child is the child node, which I'm assuming would be this guy. The right child is the deletion location, which would be the tail. It's 12, isn't it? Yeah. Okay, let me just see if I can run through this. If the left child num keys is greater than or equal to the right child, so it's not, so it should be this guy. All right, with the 3 keys, it should be that. And then B tree new parent equals left child tail previous. New parent is the left child tail. Oh, sorry, it's this one, isn't it? New parent is equal to the right child head. Yeah, okay, that's a pretty good start. The new parent old child is equal to the new parent child, so the null. Remove key the right child, the new parent. So remove this new parent from the right child. Fair enough. Insert key before key. The deletion node. The deletion node. The deletion node. Ah, wait, to be fair, the 15 was missing, wasn't it? Sorry, I'm getting a bit distracted, but when I did this, the 15 was missing. So it knew to take the 15, it just didn't connect it properly. So I think what happened was the insert didn't do the thing correct. When I did this, I wanted to insert the new parent, that 15, into the deletion node before the deletion location. The deletion location was the tail. I want to insert the 15 right before there. So it was trying its best. Insert behind previous. Would previous be null at that point? I forget. Would previous be null? Because the 14, I think, would have been deleted already. Wouldn't it? I think it's a weird case where because there's only one thing left, something very strange has happened. Current tree previous. There wouldn't be any previous. So I think, see, the issue is that the current node head would be pointing to current key next, I think. I think the head is pointing to the tail, which maybe is okay, but it's a little bit not quite what I was hoping for. Anyway, so bearing that in mind, when you call insert key before key, so I think the removal worked because the 15 isn't there anymore. The removal did work. But then insert key before key, if previous, I'm gonna say one more thing I will do. Maybe I'll just quietly do it. Oh, I did set it to null, which means it'll probably be. So I think this won't happen. I think it'll be this one. Key to insert. Next will be the insert behind. Yeah, see, I forgot to do one extra thing. I forgot to say node head is equal to the key to insert. This might genuinely be the fix. Yeah, there you go. 15. Sorry, delete the 14. 15, 2, 9, and then 21, 103. Wow, okay. There's definitely other bugs for sure. There's no way I did a midnight scramble like this and did it correctly. but it's not bad. It's not a bad sort of. It's not a bad scramble. The code is a bit ugly though. I can't lie. At least I made some helpers. I was smart, but they're oddly specific. Move key to head isn't too bad. Move key to tail isn't too bad. This is a bit strange. This is not too bad. And this is weird. This is a weird function. Alright, I mean, I can do a bit more debugging, but I think I'm pretty much done with B-trees. The ideas are there, I just don't know if I implemented it perfectly. The other major, or not even major, the other thing I could do is also just have a command line argument to set the max keys and the min key. Well, min keys is decided, but the max keys, I can do a command line argument for that. God, it's ugly. But it half works, which is pretty good.